Have you ever looked up at the night sky and felt a strange, deep sense of wonder, a quiet suspicion that the universe is whispering secrets we're only beginning to hear? That behind the chaos of stars, galaxies, and even our own fleeting lives, there's something more, something structured, something intentional. It's a feeling as ancient as humanity itself, an intuition that the cosmos isn't random, but woven together by hidden patterns, elegant codes, and mysterious laws we're only just starting to decode. From the spiraling arms of distant galaxies to the rhythmic cycles of nature, and even the seemingly coincidental moments in our own days, what if nothing is truly accidental? What if everything is connected by an invisible architecture, an order so profound it defies our current understanding of reality? That's exactly what we're diving into today. In this video, we'll explore 30 of the most fascinating theories about the universe's hidden patterns, ideas that stretch from the edges of theoretical physics to the heart of philosophy and beyond. These aren't just abstract concepts, they're windows into how reality might truly operate. Some suggest the cosmos operates like a cosmic computer, running on algorithms we haven't yet cracked. Others propose that time, space, and even consciousness are interwoven in a grand symphony of meaning, and a few even hint that what we perceive as chance might actually be the subtle fingerprints of something far more extraordinary at work. This isn't about having all the answers, it's about asking better questions and marveling at just how mysterious and how breathtakingly organized our universe might actually be. So whether you're a curious skeptic, a science enthusiast, or someone who's always felt there's more to existence than meets the eye, you're in the right place. This journey is for anyone who's ever wondered why certain numbers repeat throughout nature, why galaxies form in similar shapes across billions of light years, or whether there's a deeper rhythm to reality itself. We'll venture beyond what's familiar and comfortable into a realm of possibility that challenges everything we think we know. By the end, you may not have all the answers, but you'll see the cosmos in a whole new light. So settle in, open your mind, and let's begin. And where better to begin than with a theory so profound it challenges the very nature of our dimensional existence, the holographic principle. This idea proposes that everything we perceive in our three-dimensional world, from the coffee cup on your desk to the vast, sprawling galaxy clusters, might actually be a projection from a flat, two-dimensional surface. It's the ultimate cosmic illusion, suggesting reality as we know it is a kind of incredibly detailed and convincing hologram. This isn't science fiction. It's a serious hypothesis that emerged from one of the most perplexing paradoxes in modern physics, centered on the most destructive objects in the universe, black holes. The story starts with a brilliant insight from physicist Jacob Bekenstein and the legendary Stephen Hawking. They discovered that black holes, despite supposedly destroying everything that falls in, have entropy, a measure of information and disorder. Even more strangely, this entropy wasn't proportional to the black hole's volume, as you might expect, but to the surface area of its event horizon. This was a huge clue. It implied that all the information describing everything that ever fell into a black hole wasn't lost inside its infinite depth, but was instead somehow encoded on its two-dimensional boundary, like data etched onto the surface of a sphere. The universe, it seemed, was playing a trick on us, storing 3D information on a 2D surface. This revelation led theorists like Gerard T. Hooft and Leonard Susskind to a breathtaking extrapolation. If it's true for a black hole, could it be true for the entire universe? The holographic principle was born from this question. It posits that our entire cosmic reality might be a projection from a distant, flat surface, much like a 3D hologram is projected from a 2D film plate. Every event, every particle, every force we experience here is just a translation of information encoded on this fundamental boundary at the edge of the universe. You, me, everything we see and feel would be a shimmering, dynamic illusion, a cosmic shadow play of incomprehensible depth and complexity. The implications are enough to make your head spin. If this principle is correct, it suggests that the fundamental building blocks of reality aren't matter or energy, but bits of information. The universe would essentially be computational, a cosmic data processing system where the laws of physics are simply the software code. It provides a potential path to unify the two great pillars of modern physics, quantum mechanics and general relativity, by suggesting that gravity itself emerges from this quantum information stored on the lower dimensional boundary. It's a theory that doesn't just add to our understanding, it completely reframes the stage upon which the laws of physics perform. We are left to wonder if the solidity of the world is the ultimate deception, and that at its heart, reality is nothing more and nothing less than a magnificent and meaningful pattern of information. But if the holographic principle suggests reality is an information-based illusion, our next theory tackles an even grander stage for that illusion to play out on. It asks a question that redefines the very meaning of everything. What if our universe, with its specific laws and constants, isn't the only one? What if it's just a single bubble in a frothing, infinite ocean of universes, each with its own unique physics? This is the stunning proposition of cosmic inflation and the multiverse, a concept that begins with the very first moments of existence. To understand this, we need to rewind time back to a fraction of a second after the Big Bang. The standard Big Bang model has some problems. It can't explain why the universe is so remarkably uniform in all directions, or why space appears so flat on the largest scales. To solve these puzzles, physicist Alan Guth proposed a radical idea: cosmic inflation. He suggested that the newborn universe underwent a brief, unimaginably violent period of hyper-expansion, doubling in size over and over again in a time span so short it makes a nanosecond look like an eternity. This inflationary burst smoothed everything out, ironing out any wrinkles and setting the stage for the more gentle expansion we see today. Now, here's where it gets truly wild. According to quantum physics, empty space is never truly empty. It's a seething, bubbling foam of quantum fluctuations where particles and energy pop in and out of existence. During that incredibly brief period of inflation, these tiny quantum jitters would have been stretched to astronomical sizes. These imperfections became the seeds for all the structure we see in the cosmos today. The grand web of galaxies, the clusters, and the vast voids between them. The universe we see is literally a magnified quantum fluctuation, but the most profound implication is what we don't see. The leading theory suggests that inflation isn't a one-time event that started and stopped everywhere at once. Instead, it's more like a never-ending chain reaction. Think of the multiverse as a constantly boiling pot of water. Our entire observable universe is just one bubble that formed in that foam. Inflation ended inside our bubble, allowing galaxies and life to form, but outside of our bubble, the inflationary energy continues to stretch space-time. In that eternally inflating background, new bubbles are constantly nucleating, each one a new universe budding off with its own Big Bang. And this is where the hidden pattern becomes truly mind-bending. The physical laws and constants we take for granted, the strength of gravity, the mass of an electron, the very number of dimensions, might not be fundamental truths etched into the cosmos. They could simply be local bylaws, the accidental outcome of how our particular bubble formed. In another universe, gravity might be repulsive, atoms might never form, or time might run backwards. An infinite multiverse implies that every possible configuration of physical reality exists somewhere. In this breathtaking vista, our universe isn't fine-tuned for life. We simply exist in one of the rare bubbles where the random dice roll of physics allowed complexity and consciousness to emerge. We are not the center of the cosmos, but merely one possibility in an infinite tapestry of existence. And if the multiverse offers a staggering array of possible realities, our next theory provides a potential framework for how any one of those realities could be built. It's a concept that takes us from the impossibly vast to the almost impossibly small, proposing that at the very foundation of everything, there are no point-like particles but tiny, vibrating loops of energy. This is string theory, and its most profound suggestion is that our universe is not made of 3 dimensions of space and 1 of time, but of many more, perhaps 10 or 11 in total, all woven together in a delicate cosmic symphony. For centuries, we've pictured the fundamental building blocks of matter, like electrons and quarks, as infinitesimal dots, points with no internal structure. But this picture creates a huge problem for physics. When you try to apply the rules of quantum mechanics to gravity, the math completely breaks down, producing nonsensical infinities. String theory elegantly sidesteps this problem by proposing that these aren't points at all. Instead, the most basic entities are unimaginably small, one-dimensional strings, so tiny that if an atom were the size of our solar system, a string would be about the size of a tree on Earth. And just like a violin string can vibrate to produce different notes, a G, a B, a high C, these cosmic strings vibrate at different frequencies. One specific vibration pattern might give rise to an electron, another to a photon, another to a quark. In this breathtaking vision, every particle and every force is simply a different note on the same fundamental instrument. The universe isn't a collection of separate things, it's a composition, a melody played on these tiny, vibrating loops. This beautiful idea, however, comes with a monumental catch. The mathematics of string theory only works if the universe has more dimensions than the 4 we directly experience. To avoid mathematical chaos, the equations require either 10 or 11 dimensions. This immediately raises an obvious question. If they exist, where are these extra dimensions? Why can't we see them or move through them? The leading answer is a process known as compactification. Imagine a long, stretched-out garden hose. From a great distance, it looks like a simple one-dimensional line. But if you get very close, you discover it actually has a second dimension, a circular dimension curled up into a tiny, tiny tube. In the same way, theorists propose that at every single point in our familiar 4-dimensional spacetime, there are 6 or 7 additional spatial dimensions, but they are curled up into an infinitesimally small, intricate shape called a Calabi-Yau manifold. These dimensions are so profoundly compactified, so tightly wound upon themselves at the Planck scale, that they are completely hidden from our everyday perception and even our most powerful particle colliders. The fabric of reality has a hidden texture, a microscopic complexity that dictates the very laws of physics we observe. This is where string theory makes its grandest promise: unification. The theory naturally contains a particle with the exact properties of the graviton, the hypothetical carrier of the gravitational force. For the first time, gravity is brought into the quantum fold, not as a troublesome outsider, but as an intrinsic part of the theory. String theory doesn't just aim to describe particles, it seeks to be a theory of everything, a single, self-consistent framework that explains all fundamental forces and all matter under one elegant mathematical roof. The different vibrations of the strings would give rise not only to particles but also to the forces that govern them, weaving together the fabric of spacetime itself with the matter within it. The hidden pattern here is one of ultimate harmony, suggesting that the universe's apparent complexity emerges from an underlying simplicity, a tiny, vibrating string dancing in a higher dimensional space. But this breathtaking vision of countless universes raises a deeply philosophical question that brings us right back to our own existence. If the laws of physics are just a random cosmic lottery ticket, why did we get so incredibly lucky? Why does our universe have such a perfect, delicate balance of constants that allows for stars, planets, and ultimately us? This puzzle is the heart of the anthropic principle, a concept that is both profoundly simple and deeply controversial. It suggests that the universe appears finely tuned for life for one very straightforward reason: we are here to observe it. It's a statement that seems almost too obvious, yet its implications ripple through cosmology, physics, and philosophy, forcing us to reconsider our place in the cosmos. We can explore this idea through two main lenses, often called the weak and strong anthropic principles. The weak anthropic principle is the less controversial of the two. It's essentially a selection effect, a statement about our position as observers. It argues that we shouldn't be surprised to find ourselves in a universe that permits our existence. Of course, we observe constants like the strength of gravity or the mass of an electron to be precisely set to allow for carbon-based life. If they were even slightly different, we wouldn't be here to notice. Imagine a puddle of water waking up one morning and marveling at how perfectly the hole it sits in is shaped to accommodate its form. The puddle thinks the hole was designed just for it, but in reality, it simply fills the available space. In the same way, the weak anthropic principle suggests we are the puddle and our universe is the hole. We aren't seeing a designed universe, we are simply seeing the only kind of universe we could possibly find ourselves in. This reasoning is powerfully supported by the multiverse concept, where an infinite number of universes with different laws exist, and we, by definition, inhabit one of the rare, life-friendly ones. Then there's the strong anthropic principle, which takes a much more radical and contentious leap. This version proposes that the universe must, in some sense, have properties that allow life and consciousness to develop. It's not just a happy accident we stumbled upon, it's a prerequisite for reality itself. Some interpretations of this strong version edge into the territory of a participatory universe, where the act of observation is somehow necessary to bring the cosmos into being. The most famous proponent of this view was physicist John Archibald Wheeler, who suggested we live in a participatory universe where observers are required to give the universe its tangible existence. In this view, the fine-tuning isn't just a curious fact, it's a fundamental feature, as if the universe knew we were coming. This strongly anthropic reasoning often gets intertwined with religious or teleological arguments, suggesting a purpose or a goal behind the cosmos, which is why it remains on the fringes of mainstream science for many. The debate between these views often centers on the cosmological constant, a number that represents the energy density of empty space. This constant is fine-tuned to an almost absurd degree of precision. If it was slightly larger, the universe would have blown itself apart too quickly for galaxies to ever form. If it was slightly smaller, the universe would have collapsed back in on itself almost immediately. The value we observe is perfectly poised between these two catastrophes. To some, this is the strongest evidence for a multiverse. We just got lucky. To others, it's a hint of something deeper, a law or principle we don't yet understand that necessitates life. The anthropic principle forces us to confront the limits of our scientific inquiry. Are the constants of nature truly free parameters, or are they the only possible values locked in by a deeper, undiscovered theory? It remains one of the most compelling and humbling ideas in modern cosmology, a constant reminder that our observation of the universe is not a passive act, but is inextricably linked to the reality we seek to understand. But if the anthropic principle makes us question our role as observers, quantum entanglement forces us to question the very nature of reality itself. This is a phenomenon so bizarre that even Albert Einstein famously dismissed it as spooky action at a distance, a phrase that perfectly captures its unsettling defiance of common sense. At its heart, entanglement describes a profound connection between particles, a bond that transcends the vast emptiness of space and operates outside the flow of time as we know it, creating a kind of instant cosmic communication that seems to break all the rules. To understand this spookiness, let's consider a simple, classic example. Imagine we have a special source that creates a pair of electrons. these particles are born together, interact, and then fly off in opposite directions, perhaps ending up light years apart. According to the rules of quantum mechanics, each electron's spin, a property like a tiny internal compass, isn't fixed until it's measured. Before a measurement, each particle exists in a fuzzy cloud of all possible states, a superposition of both spinning up and spinning down simultaneously. This is strange enough on its own, but entanglement adds a far weirder layer. These two electrons are linked, their fates are intertwined. The moment you measure the spin of the first electron and find it to be, say, up, the spin of its distant partner instantly and irrevocably becomes down. This change happens immediately, regardless of the millions of light years separating them. It's as if the universe somehow communicated the result between them faster than the speed of light, a direct violation of Einstein's theory of relativity, which states that nothing can travel faster than light. For decades, physicists argued over whether this spooky action was real or if there were some hidden variables, unknown properties set at the moment of their creation that predetermined the outcome of the measurements, making it only seem like instantaneous communication. This debate was finally settled in the 1960s by physicist John Bell, who devised a brilliant mathematical test now known as Bell's theorem. His inequalities provided a way to experimentally distinguish between a universe with hidden local variables and one with true, non-local quantum weirdness. Over and over again in laboratories around the world, these experiments have confirmed the quantum view. There are no hidden signals, the connection is real and instantaneous. The particles are not communicating, they are simply acting as a single, unified system. A single entity that just happens to have parts that are separated by a great distance. This non-locality suggests that at the most fundamental level, the universe is not a collection of separate, independent things but is deeply, holistically interconnected in a way we are only beginning to fathom. This radical interconnectedness hints at a hidden pattern in the cosmos that is far more profound than simple cause and effect. If entangled particles can coordinate their behavior across any distance without any exchange of information, it implies that space itself might be an emergent property, not the fundamental stage we assume it to be. 2 points separated by a billion light years might not be as separate as they appear from our limited classical perspective. Some interpretations, like the holographic principle we discussed earlier, find a natural home for this idea, suggesting that the information describing these entangled particles is stored together on a shared lower dimensional boundary, making their connection less mysterious from that vantage point. Others see it as evidence for a deeper level of reality, a quantum substrate where what we perceive as vast distances are simply illusions. The implications of this for a hidden cosmic architecture are staggering. Could entanglement be the invisible thread weaving the entire universe together? Some theorists speculate that in the very first moments after the Big Bang, everything in the nascent cosmos was in intimate contact. As the universe expanded inflationarily, these regions were pushed far beyond each other's light horizons, yet they may have retained their primordial quantum connections. This could explain the uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang, which shows the same temperature in all directions, even though those regions have never been in causal contact according to standard physics. They appear to have been in contact somehow, and quantum entanglement provides a potential mechanism for that coordination, a ghostly handshake from the dawn of time that still echoes across the cosmos. This suggests that the large-scale structure of the universe, the great cosmic web of galaxies and voids, might itself be a macroscopic manifestation of a vast, ancient quantum entanglement network. The universe isn't just expanding, it's an evolving, connected whole with its history written not just in the positions of stars, but in the invisible quantum links between them. Yet for all its ghostly influence, dark matter remains one of the greatest mysteries in all of science. We can map its gravitational shadow, but we have no idea what it's actually made of. It doesn't emit, absorb, or reflect light of any kind, hence the name dark. It seems to interact with normal matter only through gravity, making it incredibly difficult to detect directly. For decades, the leading candidate has been a hypothetical particle known as a WIMP, or weakly interacting massive particle. These particles are theorized to be heavy, slow-moving relics from the Big Bang, left over from when the universe was a seething, hot soup of primordial particles. They would interact with normal matter only through the weak nuclear force and gravity, which explains their elusiveness. Giant, ultra-sensitive detectors are buried deep underground in mines and mountains, shielded from cosmic rays, all waiting for the once-in-a-lifetime ping that might signal a WIMP collision. But so far, after years of searching, these detectors have remained silent, forcing physicists to broaden their search. This has led to a surge of interest in other compelling candidates. One particularly elegant idea is the action, a particle initially proposed to solve a completely different problem in particle physics concerning the symmetry of the strong nuclear force. Actions would be vastly lighter than WIMP, potentially 1 trillion times lighter than an electron, and would behave less like individual particles and more like a pervasive, sloshing cosmic fluid. Their detection requires a different approach, using powerful magnetic fields to potentially convert these ghostly particles into faint photons we could observe. Then there's the more dramatic possibility of primordial black holes. These wouldn't be the black holes formed from dying stars, but microscopic ones created in the intense density fluctuations of the very early universe. A sufficient number of these ancient black holes, drifting through space like unseen asteroids, could collectively account for the gravitational effects we attribute to dark matter. Each of these theories paints a different picture of the invisible universe, and the hunt to identify which one is correct is one of the most thrilling scientific endeavors of our time. But perhaps the most stunning evidence for dark matter's hidden architecture isn't found in a lab, but written across the sky in the grandest pattern of all, the cosmic web. Supercomputer simulations that model the evolution of the universe, starting with the near-uniform soup of the Big Bang and adding the gravitational pull of dark matter, produce a structure that is eerily familiar. They show a vast, interconnected network of filaments, a cosmic spiderweb stretching across billions of light years, with gigantic galaxy clusters forming at the dense intersections and immense voids lying between them. This is exactly what our most powerful telescopes observe when they map the universe in 3 dimensions. This cosmic web is not primarily shaped by the visible galaxies and gas. It is sculpted by the unseen gravitational wells of dark matter. The normal matter, the stuff we are made of, simply flowed into the gravitational valleys that dark matter carved out first. We are literally surfing on the waves of an invisible ocean, our entire visible universe tracing the outline of a hidden architecture we cannot see. But while dark matter sculpts the cosmic web through its relentless gravitational pull, an even more mysterious and dominant force is working in the opposite direction, not pulling the universe together, but actively and violently tearing it apart. This is the enigma of dark energy, a mysterious pressure permeating the fabric of space itself that is causing the expansion of our universe to not just continue, but to accelerate at an ever-increasing rate. Its discovery was so shocking and unexpected that it completely upended our understanding of cosmic destiny, forcing us to confront a reality where the future of everything is far stranger and more desolate than we ever imagined. The story of this discovery begins with a simple question: what is the ultimate fate of the universe? For most of the 20th century, cosmologists were locked in a debate between 2 possibilities. Would the combined gravity of all the matter in the cosmos eventually halt the expansion from the Big Bang and pull everything back together in a fiery, big crunch? Or was the universe's initial velocity just enough to keep it expanding forever, slowly and steadily cooling into a dark, frozen void? The answer hinged on precisely measuring how the expansion rate had changed over cosmic time. To do this, two rival teams of astronomers in the late 1990s turned to a specific kind of stellar explosion, a Type 1, a supernova. These are not just any exploding stars, they are cosmic standard candles. Because they always explode with roughly the same peak brightness, astronomers can measure how bright they appear from Earth and use that to calculate their exact distance with incredible accuracy. Furthermore, by analyzing the redshift of their light, we can measure how much the universe has stretched since the moment of the explosion. The teams were expecting to confirm the universe was slowing down, its expansion gradually braked by the gravitational tug of all matter, both dark and visible. Instead, they found the opposite. The most distant supernova, whose light had been traveling to us for billions of years, were significantly dimmer than their redshifts predicted. This could mean only one thing: these stars were much farther away than anyone had thought. The universe wasn't slowing down at all, its expansion was speeding up. Some mysterious repulsive force acting against gravity was pushing galaxies apart with ever-increasing ferocity. This revelation was so paradigm-shattering that it earned the leaders of the two teams the Nobel Prize in Physics in 2011. The universe, it seemed, had been hiding its biggest secret in plain sight. So what is this dark energy? The leading and simplest explanation is one that Einstein himself conceived of and then famously discarded as his greatest blunder: the cosmological constant. In his equations for general relativity, Einstein found that they naturally allowed for a term, represented by the Greek letter lambda, that describes a constant energy density inherent to the vacuum of space itself. This vacuum energy would have a repulsive gravitational effect, causing empty space to push itself apart. At the time, Einstein introduced it to force his equations to describe a static, unchanging universe, which was the prevailing belief. When Edwin Hubble later discovered the universe was actually expanding, Einstein abandoned the idea. But modern quantum physics gives this concept new life. It tells us that the vacuum of space is not truly empty. It is a seething, bubbling sea of virtual particles constantly flickering in and out of existence. This quantum foam should theoretically generate a tremendous amount of vacuum energy, a cosmological constant. There's just one colossal problem. When physicists calculate how much energy this quantum vacuum should contain, the predicted value is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the largest discrepancy between theory and observation in all of science. This cosmological constant problem remains perhaps the deepest unsolved mystery in fundamental physics, suggesting our understanding of the quantum vacuum is profoundly incomplete. Because of this huge problem, many theorists have proposed alternative models. Perhaps dark energy isn't a constant after all, but a dynamic force that has changed over the life of the universe. The most prominent of these ideas is quintessence, named after the fifth element of ancient Greek philosophy. Quintessence postulates a mysterious, dynamic energy field that permeates all of space. Unlike the static cosmological constant, a quintessence field could evolve over time, its energy density increasing or decreasing. In some models, it could even interact weakly with normal matter. This opens up a range of bizarre possibilities for the far future. If the strength of dark energy were to increase over time, it could lead to a catastrophic end scenario known as the Big Rip. In this fate, the accelerating expansion would eventually overcome all forces, first tearing apart galaxy clusters, then galaxies themselves, then solar systems, stars, planets, and finally, in the last fraction of a second, ripping apart atoms and the very fabric of spacetime. It's a truly apocalyptic vision of an end driven not by gravity, but by the repulsive energy of nothingness itself. The discovery of dark energy and its accelerating push fundamentally rewrites the ultimate fate of the cosmos. The once popular dream of a big crunch, a cyclical universe of endless contraction and rebirth, now seems off the table. Instead, the current evidence points toward a far more lonely and silent conclusion, a heat death or big freeze. In this scenario, the acceleration continues unabated. Distant galaxies will first redden, then fade from view as the space between us and them expands faster than light can travel across it. Our observable universe will shrink to include only our local group of gravitationally bound galaxies, all else lost behind an impenetrable curtain of darkness. Over trillions of years, stars will burn out, galaxies will evaporate, and matter itself may decay. The universe will become an ever-cooling, ever-expanding, supremely empty void, a desolate expanse where the last embers of heat and light fade into an eternal, uniform cold. Dark energy, this mysterious force we are only beginning to name, appears to be the author of this final, silent chapter, its hidden pattern one of relentless, exponential isolation written into the vacuum of space itself. This leads us to a theory so audacious it questions the very substance of reality, suggesting that the universe isn't just described by mathematics, it is mathematics. This is the mathematical universe hypothesis, championed by physicist and cosmologist Max Tegmark. It's a perspective that dissolves the boundary between the abstract world of numbers and equations and the tangible, physical world we inhabit. If this hypothesis is correct, then every single thing in existence, from the electrons dancing around an atom to the vast, swirling galaxies, is not just governed by mathematical laws, but is itself a mathematical structure. You, the device you're watching this on, and the space between us are all ultimately mathematical objects interacting with other mathematical objects in a grand, abstract symphony of logic. To grasp this mind-bending concept, we need to reconsider what we mean by reality. We typically think of the physical world as the primary reality, and mathematics as a wonderfully effective human invention, a language we created to describe and model that world. But Tegmark inverts this relationship entirely. He proposes that mathematical existence and physical existence are one and the same. A mathematical structure, in his view, is simply a set of abstract entities with relations between them. Think of something as simple as the set of whole numbers 1, 2, 3, and so on, with relations like addition and multiplication. This structure exists in a timeless, unchanging, abstract sense. It doesn't need a physical universe to exist. Its existence is inherent in its logical consistency. Now, if you have a mathematical structure complex enough to contain self-aware substructures, subsets of the structure that can perceive themselves and their environment, then those substructures will subjectively experience themselves as living in a physical world. In other words, our conscious experience is what it feels like to be a complex pattern of information processing inside a giant mathematical object. The implications of this are staggering. It suggests that every possible mathematically consistent universe actually exists. Our particular universe, with its specific set of physical laws and constants, is just one of a vast, perhaps infinite, ensemble of mathematical structures. Some of these structures might be simple, like the whole numbers, and contain no self-aware observers. Others might be impossibly complex, with laws of physics utterly alien to our own. We find ourselves in this particular mathematical structure not because it's special, but because it's one of the structures complex enough to allow for our existence. This echoes the anthropic principle we discussed earlier, but frames it in a purely mathematical context. We don't observe the laws of physics we do because they were fine-tuned. We observe them because they are the properties of the particular mathematical structure we are a part of. The fundamental ingredients of reality aren't particles or forces, but numbers, sets, and equations. This hypothesis provides a potential answer to the most profound question in physics. Why is mathematics so unreasonably effective in describing the natural world? From the elegant orbits of planets described by Newton's equations to the bizarre predictions of quantum mechanics that are confirmed to a dozen decimal places, math works with an accuracy that borders on the miraculous. If the universe is inherently mathematical, then this effectiveness is no longer a mystery. Of course, a mathematical structure behaves in a way that is perfectly described by mathematics. That's all it is. We aren't discovering the laws of physics, we are discovering the properties of the mathematical structure we are embedded in. The physicist is not an explorer charting unknown physical territory, but a mathematician uncovering the theorems of their own native reality. Yet, for all its elegance, the mathematical universe hypothesis is not without its criticisms and profound philosophical puzzles. The most immediate question is, what breathes fire into the equations? Why should a mathematically consistent structure automatically manifest as an experienced reality? This is known as the reality problem. Tegmark's answer is a form of radical Platonism, asserting that all consistent mathematical structures exist in a mind-independent way, and that existence is simply mathematical existence. Another major challenge is the question of consciousness. How does a self-aware substructure within a mathematical object arise? How does a specific pattern of information processing, no matter how complex, generate the subjective, qualitative experience of being the redness of red, the feeling of wonder? This is the infamous hard problem of consciousness, and the hypothesis doesn't so much solve it as relocate it into the abstract realm. Despite these deep questions, the mathematical universe hypothesis remains one of the most compelling and ultimate visions of a hidden cosmic pattern. It proposes that at the bedrock of everything beyond space, time, and even physicality lies the timeless, unchanging, and breathtakingly beautiful world of mathematics. But if the universe is a mathematical structure, what kind of pattern might it be following? One of the most visually stunning and mathematically rich candidates is the fractal, a shape of infinite complexity, built from repeating patterns that look similar at every scale of magnification. This leads us to an enthralling possibility that the cosmos itself, in its grand architecture, is fundamentally fractal. Fractal cosmology proposes that the universe isn't just described by fractal mathematics, but that it actively embodies these principles, displaying self-similar patterns from the smallest quantum realms to the largest clusters of galaxies. It's a theory that suggests the cosmos has a hidden, recursive order, a signature of scale invariance written into the very fabric of existence. To understand this, we first need to grasp what a fractal is. Imagine a fern leaf. Look at it from a distance and you see a certain complex shape. Now, pluck one smaller leaf from that fern, and you'll notice it has the same overall shape as the whole plant. Break off a single tiny leaflet from that smaller leaf, and again the pattern repeats. This is self-similarity, the characteristic feature of a fractal, where the same intricate form appears regardless of how far you zoom in or out. This isn't just a biological curiosity, it's a mathematical phenomenon famously captured by the Mandelbrot set, an infinitely complex boundary generated by a deceptively simple equation. Where Euclidean geometry deals with perfect smooth lines, circles, and cubes, fractal geometry describes the rough, fragmented, and infinitely detailed patterns found throughout nature, in coastlines, clouds, trees, and snowflakes. For decades, astronomers assumed the universe was essentially smooth and homogeneous on the largest scales. This cosmological principle, a cornerstone of modern cosmology, states that if you look at the universe on a sufficiently grand scale, say beyond a few 100 million light-years, matter should appear evenly distributed no matter where you look. This smoothness is a key prediction of the inflationary Big Bang model, but a handful of scientists, most notably the cosmologist Luciano Pietranero, began to challenge this view in the 1980s. When they analyzed the data from the earliest large-scale galaxy surveys, they argued that the distribution of matter didn't appear to smooth out. Instead, they saw clusters of galaxies forming larger clusters, which in turn were part of immense superclusters, all arranged along vast, interconnected filaments with huge, empty voids between them. This cosmic web, they argued, looked less like a homogeneous soup and more like a fractal pattern, with structures repeating across multiple scales. The debate hinges on a specific mathematical measurement, the correlation function. This measures how likely you are to find another galaxy at a given distance from any random galaxy. In a smooth, homogeneous universe, this correlation should drop to zero at large scales, meaning the position of one galaxy tells you nothing about the position of another galaxy very far away. But if the universe is fractal, the correlation should follow a power law, showing that clustering exists across all observable scales. Early analyses by Pietranero and his colleagues suggested this power law behavior persisted, implying the universe was fractal as far as we could see. Mainstream cosmology, however, points to more recent and precise data from surveys like the Sloan Digital Sky Survey. This data shows that while the universe is undoubtedly fractal-like and clustered up to a certain scale, around a few 100 million light-years, the correlation function does indeed break down and flatten out on the very largest scales. The current consensus is that the universe transitions from a fractal-like state to a smooth, homogeneous one, but the precise scale of this transition and its implications remain a rich area of study. This doesn't mean fractal concepts are irrelevant to cosmology, far from it. Even if the entire universe isn't a perfect fractal, these principles are powerfully at work within it. The cosmic web itself is a stunning example of fractal geometry in action. The branching patterns of galaxy filaments with clusters nesting within larger clusters mirror the structure of a neural network or a lightning bolt. Furthermore, the initial seeds for all this structure are believed to be quantum fluctuations, tiny, fractal variations in the density of the primordial universe that were stretched to cosmic proportions during inflation. The pattern of the hot and cold spots in the cosmic microwave background radiation, the afterglow of the Big Bang, also exhibits a form of scale invariance, its fluctuations following a pattern that is almost but not perfectly fractal. This near-scale invariance is a key prediction of inflation and is one of the theory's strongest supporting pieces of evidence. The implications of a fractal universe would be profound. It would suggest a cosmos without a center and without an edge, a system of infinite complexity where the laws of physics might operate differently at different scales. It could provide a new framework for understanding gravity and the distribution of matter, potentially offering alternatives to our standard models. Most philosophically, a fractal cosmos reflects a deeply elegant and parsimonious design, a universe that builds its overwhelming complexity from the repetition of a simple underlying pattern. It hints at a fundamental process of recursion in the laws of physics, where the same simple rules are applied over and over again to generate the rich tapestry of reality we observe. Whether the universe is a perfect fractal or not, the presence of these self-similar patterns across such vast scales is a breathtaking clue, pointing toward a hidden order that is both mathematically beautiful and intimately woven into the structure of everything we see. From the invisible scaffolding of dark matter to the abstract beauty of mathematical structures, we've explored patterns that suggest a cosmos built on logic and information. But what if the most fundamental ingredient of all isn't out there in the equations, but in here, in our own experience? This brings us to one of the most speculative and profound frontiers of cosmology, the idea that consciousness might not be a rare byproduct of complex brains, but a fundamental property of the universe itself. This isn't about ghosts or spirits. It's a serious, though highly controversial, line of philosophical and scientific inquiry that seeks to solve the hard problem of subjective experience by placing it at the very foundation of reality. The most prominent of these ideas is panpsychism, a view with ancient roots that is experiencing a modern renaissance. The term comes from the Greek words pan, meaning all, and psyche, meaning soul or mind. In its simplest form, panpsychism proposes that consciousness is a universal and fundamental feature of all things. This doesn't mean that a rock is contemplative or an electron is happy. That would be a category error. Instead, it suggests that some form of incredibly rudimentary experience, what philosophers call proto-consciousness, is a basic property of matter akin to mass or charge. In this view, an electron might have a vanishingly simple, point-like experience of the world, perhaps just a bare awareness of its environment. When these simple particles combine in exquisitely complex ways, like in the human brain, these micro-experiences combine and unify to generate the rich, flowing stream of consciousness we all know. The human mind isn't creating consciousness from nothing. It's orchestrating and complexifying a property that was already there, latent in the fabric of the universe. This perspective offers an elegant, if startling, solution to the hard problem of consciousness. The hard problem, formulated by philosopher David Chalmers, asks why and how physical processes in the brain give rise to subjective experience, the redness of red, the pain of a headache, the feeling of wonder. From a standard materialist viewpoint, it's a complete mystery why such inner experiences should exist at all. Panpsychism cuts the Gordian knot by asserting that consciousness didn't emerge, it was always present. It doesn't arise from complexity. Complexity simply allows for a more sophisticated form of it. The challenge for panpsychism, often called the combination problem, is explaining how these tiny bits of experience combine into a unified whole. How do billions of neuronal micro-experiences merge to form my single, unified awareness? This is a formidable puzzle, but proponents argue it's no more mysterious than the emergence of other complex properties from simpler parts. Taking this idea to its cosmic extreme leads to an even more breathtaking possibility: cosmopsychism. This theory suggests that the universe as a whole might be conscious, a single, unified entity possessing its own form of awareness. In this view, our individual consciousnesses are not separate things that the universe generated, but are rather small, localized dissociations or aspects of the one universal consciousness. It's akin to how waves are not separate from the ocean but are patterns within it. This idea finds a curious resonance with certain interpretations of quantum mechanics, particularly the role of the observer in collapsing the wave function. The controversial Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, seemed to place consciousness at the center of reality, suggesting that a quantum system remains in a fuzzy superposition of states until it is observed or measured. This led physicist John Archibald Wheeler to his participatory anthropic principle, the idea that observers are necessary to bring the universe into being. While most modern physicists favor interpretations that don't require consciousness, like the many worlds interpretation, the allure of a conscious cosmos persists, suggesting that the universe might be engaged in a process of self-discovery through us. We are not just beings living in the universe, we are the means by which the universe knows itself, fleeting nodes of awareness in a vast conscious whole. These theories, while far from mainstream, force us to confront the deepest questions about our place in the cosmos. They challenge the assumption that matter is primary and mind is secondary, flipping the script to propose that experience might be the fundamental ground of all existence. Whether one finds these ideas inspiring or implausible, they represent a bold attempt to integrate the most intimate thing we know, our own consciousness, into our understanding of the universe's grandest patterns. They suggest that the ultimate hidden pattern might not be written in equations or dimensional folds, but in the very fabric of sentience itself. But if consciousness is indeed a fundamental feature of reality, it raises a tantalizing question about the nature of that reality itself. Could our entire universe, with all its intricate laws and conscious observers, be nothing more than an elaborate simulation running on some unfathomably advanced computer? This is the core of the simulation hypothesis, a modern idea that sounds like science fiction, but is taken seriously by a growing number of philosophers, physicists, and technologists. It proposes that what we perceive as base reality might actually be a highly sophisticated virtual construct, a kind of cosmic video game, and that we are not biological beings but simulated entities within its code. The most famous philosophical argument for this idea comes from Oxford philosopher Nick Bostrom, who framed it as a stark trilemma, a set of three possibilities, one of which he argues must almost certainly be true. The first proposition is that almost every civilization at our level of technological development goes extinct before it can develop the capability to run realistic ancestor simulations. This is a rather bleak outlook, suggesting that some great filter, like nuclear war or environmental collapse, always wipes out species like ours before they can reach a post-human stage. The second proposition is that even if advanced civilizations do survive, they are extremely unlikely to run a significant number of simulations of their own evolutionary history. Perhaps they would find it ethically dubious, technologically impractical, or simply uninteresting to simulate primitive beings like us. The third and most discussed proposition is that we are almost certainly living in a simulation right now. Bostrom's logic is statistical. If even one advanced civilization survives and chooses to run such simulations, they could potentially create astronomical numbers of them, perhaps billions or trillions. The number of simulated minds would vastly outnumber the few biological ancestors in the original reality. Therefore, if you are a conscious mind, the odds are overwhelmingly greater that you are one of the simulated ones rather than an original biological being. It's a cosmic numbers game that is incredibly difficult to refute. Beyond this philosophical reasoning, some have looked for potential scientific evidence, glitches in the matrix, so to speak. One line of inquiry stems from the world of video games. In any simulation, the computing power is finite. To save processing resources, a simulator would likely not render every single detail of reality in high resolution all the time. Instead, it would use a technique called level of detail, generating fine details only when they are being observed. This is exactly how modern game engines work. The lush forest in the distance is just a low-resolution texture until you walk closer. Could our universe operate on a similar principle? Some interpretations of quantum mechanics, particularly the Copenhagen idea that a particle doesn't have a definite state until it is measured, seem eerily reminiscent of this. Reality appears to resolve or render only upon observation, which could be interpreted as a resource-saving technique. Furthermore, our universe appears to have fundamental limits and a finite resolution, much like a digital simulation. There is a smallest possible unit of space, the Planck length, and a smallest possible unit of time, the Planck time, suggesting reality might be pixelated rather than perfectly smooth. The speed of light could be seen as the processing speed limit of the cosmic computer, a maximum rate at which information can be updated across the simulation. The concept also finds a curious partner in the digital physics movement, which we touched on with the holographic principle. If the universe is fundamentally made of information, then it operates like a computer. The laws of physics are simply the algorithms that govern how that information is processed and changed. In this view, the universe isn't just like a computer, it is a computer. The simulation hypothesis takes this a step further, suggesting that if our reality is computational, then it could very well be a program running on a computer built in a higher-level reality. This doesn't necessarily answer the question of what created that higher reality, but it does open the door to a potentially infinite regress of simulations within simulations, a nesting doll of existences, each believing itself to be the one true base reality. Of course, the hypothesis is met with significant skepticism and profound philosophical objections. The most common retort is that it is an untestable and therefore unscientific proposition. How could we ever prove we are in a simulation if the simulators control all the rules and could easily reset or alter any experiment we devise? Others argue that the computational power required to simulate every particle and every conscious experience in a universe of our size and age would be absurdly, impossibly vast, far exceeding any conceivable technology. Yet, proponents counter that we cannot presume to understand the limits of a civilization potentially millions of years more advanced than our own. Their physics and computing paradigms might be as incomprehensible to us as a supercomputer would be to a bacterium. Furthermore, a simulator wouldn't need to simulate the entire universe in perfect detail, only the parts that are being observed, much like the loaded areas in a video game. The deepest objection is perhaps existential. If this is a simulation, does it make our lives, our struggles, and our loves any less real? If we are lines of code, our experiences are still genuine to us. The pain we feel is real pain, the joy is real joy. The simulation, for all its artificial origins, would be the only reality we have ever known or will know, making its moral and emotional weight no less significant. It stands as one of the most provocative and mind-expanding ideas in modern thought, forcing us to question the very substrate of our existence and our place in a cosmos that might be far stranger than we ever dreamed. But if our reality is a simulation, it runs on a fundamental rule that governs not just information but change itself, a principle that gives our existence a direction and an inevitable conclusion. This brings us to one of the most palpable and persistent patterns we all experience, the relentless one-way flow of time. We remember the past but not the future. We grow older, never younger. Eggs scramble but never unscramble. This universal asymmetry is known as time's arrow, and its origin is one of physics' greatest puzzles. Surprisingly, the answer doesn't lie in the laws of motion, which work perfectly fine in reverse, but in the statistical behavior of countless particles and a concept known as entropy. To understand entropy, think of a brand new deck of cards. It comes perfectly ordered, all the suits together, all the numbers in sequence. This is a low entropy state, a condition of high order and low probability. Now, if you shuffle that deck thoroughly, you create disorder. The cards become randomly mixed. This is a high entropy state, which is vastly more probable because there are almost countless ways for a deck to be disordered, but only a few ways for it to be perfectly ordered. Entropy is simply a measure of this disorder, and the second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It never spontaneously decreases. This is why your room gets messy if you don't clean it, why ice melts in your drink, and why perfume spreads to fill an entire room. The universe has a built-in preference for disorder, and this constant increase is what gives time its arrow. The future is the direction in which entropy increases. This presents a colossal mystery known as the past hypothesis. The second law tells us that entropy increases toward the future, but it must have been even lower in the past. So why was the entropy of the early universe so astonishingly low? Imagine the Big Bang not as a chaotic explosion, but as the ultimate act of cosmic organization. The universe began in an exquisitely ordered, low-entropy state, a state of incredibly smooth and uniform density. This is the most profound puzzle in all of cosmology. Why did the universe start with this cosmic winning lottery ticket, a state of such improbable order that it has been fueling the increase of entropy, and thus the flow of time itself for the last 13.8 billion years? We are all, in a sense, living in the aftermath of this breathtakingly special beginning, riding the wave of disorder that it set into motion. Theorists have proposed several compelling ideas to explain this low entropy origin. One possibility is that our observable universe is just a tiny fluctuation within a much larger and older multiverse that is typically in a state of maximum disorder or heat death. In an infinite eternity, even the most improbable events must occur occasionally through random chance. Our entire cosmic history, from the Big Bang to the eventual heat death, could be one such rare statistical fluctuation, a temporary bubble of order that will eventually dissolve back into the featureless void. It's a humbling thought. Our universe isn't special by design, but simply a rare, low-entropy accident in an otherwise lifeless and disordered eternity. Another profound idea connects the arrow of time directly to the expansion of the universe itself. As the cosmos expands, it creates ever more phase space, new possible ways for particles to be arranged. This continuous opening of new possibilities drives the increase of entropy. The gravitational collapse of matter into galaxies, stars, and black holes is actually the primary engine of entropy increase in the universe. A black hole, it turns out, possesses an enormous amount of entropy, far more than the star that formed it. So the formation of structure isn't fighting against the universe's trend toward disorder. It is the very mechanism by which that disorder is achieved on a cosmic scale. The arrow of time, the expansion of space, and the growth of structure are all inextricably linked parts of the same cosmic process, all stemming from that mysterious low-entropy starting point. Our experience of time's relentless forward march is ultimately a manifestation of the universe's ongoing quest to fulfill its thermodynamic destiny. But this smooth, continuous fabric of spacetime that Einstein described so beautifully might itself be an illusion, a kind of cosmic mirage that breaks down when we peer into the heart of reality at the very smallest scales. To reconcile the colossal success of general relativity with the bizarre rules of the quantum world, physicists have been forced to propose a radical new vision of the cosmos, one where the stage itself is not smooth and serene, but a churning, turbulent sea. This is the realm of quantum gravity and the mind-bending concept of spacetime foam, a theory suggesting that if we could look closely enough, the very foundations of reality would appear frothy, grainy, and wildly discontinuous. The problem at the heart of this quest is one of the greatest in all of physics. On one hand, we have general relativity, which masterfully describes the force of gravity as the curvature of a smooth, four-dimensional spacetime by mass and energy. It tells the planets how to orbit and the universe how to expand. On the other hand, we have quantum mechanics, which governs the behavior of the tiny particles that make up matter, and the other three fundamental forces, electromagnetism and the strong and weak nuclear forces. The problem is that these two pillars of modern physics are written in completely different mathematical languages and based on utterly incompatible assumptions about reality. General relativity is deterministic and smooth. Quantum mechanics is probabilistic and jumpy. When we try to apply the equations of quantum field theory to gravity, the math explodes into infinities and nonsense. This tells us that our current understanding is incomplete. We are missing the theory of quantum gravity, a framework that would describe how gravity works at the unbelievably tiny scale of the Planck length, which is about 10 to the power of -35 meters. This is where the concept of spacetime foam emerges from the work of the brilliant physicist John Archibald Wheeler. He proposed that at these minuscule Planck scales, the fabric of the universe would not be calm and continuous. Instead, the violent energy of quantum fluctuations would cause spacetime itself to writhe and churn. The geometry of space would become wildly distorted, forming a turbulent, frothy sea of tiny, short-lived wormholes, tunnels, and bubbles. In this foam, the very concepts of before and after become blurry. Cause and effect lose their meaning. The smooth, predictable stage of Einstein's universe dissolves into a probabilistic, chaotic frenzy. It's as if we've been looking at the ocean from an airplane, seeing a calm, blue surface, but quantum gravity is the view from a submarine, revealing a tumultuous, teeming world of currents and chaos just beneath. This foamy nature is driven by Werner Heisenberg's famous uncertainty principle, which states that we can never precisely know both the energy of a system and the exact time over which that energy is measured. On human scales, this uncertainty is negligible, but at the quantum level, it means that empty space is never truly empty. It is a seething, bubbling soup of virtual particles, pairs of particles and antiparticles that spontaneously blink into existence, borrow energy from the vacuum for an impossibly brief moment, and then annihilate each other, paying back the energy loan before the universe can notice. We know these particles are real because they have measurable effects, like the Casimir effect, where two metal plates placed very close together in a vacuum are subtly pushed together by the pressure of more virtual particles bouncing on the outside than can fit between them. Now apply this same quantum uncertainty to the fabric of spacetime itself. On these unimaginably small scales, the energy fluctuations are so extreme that they warp and twist the geometry of space and time, causing it to boil and foam. The universe at its heart is not a static stage but a dynamic, energetic, and fundamentally fuzzy place. The implications of this are as profound as they are strange. This foamy structure would impose a fundamental limit on the precision of all measurements. It would be impossible to measure any distance smaller than the Planck length or any time shorter than the Planck time, because the ruler you would use to measure it and the clock you would use to time it would themselves be jittering and foaming, lost in the quantum chaos. This suggests that the continuity of space and time is an emergent property, a kind of average smoothness that arises from the frenetic activity of countless tiny, discrete building blocks, much like the smoothness of water emerges from the frantic jostling of individual molecules. Some theories, like loop quantum gravity, propose that space is actually woven from tiny, finite loops or networks of spin, giving it a discrete atomic structure. The spacetime foam is the ultimate expression of this granularity, the point where the universe reveals its truly digital, pixelated nature. We are left with a breathtaking vision. The majestic, smooth continuum of spacetime that guides galaxies is at its core a storm of quantum uncertainty, a hidden pattern of turbulent creation and destruction that is the true heartbeat of reality. While the Big Bang model has become the dominant story of our cosmic origin, its reliance on a singular, infinitely dense beginning has always presented a profound mystery. What, if anything, came before it? Some theorists have proposed a breathtaking alternative that does away with the singularity entirely, suggesting our universe wasn't born from a single explosion, but from a collision, a cosmic car crash in a higher dimensional reality. This is the ekpyrotic universe model, a vision of a cyclical cosmos without a true beginning or end, where the patterns we see today are echoes of an eternal, repeating cycle. The name ekpyrotic comes from the ancient Greek word for conflagration, or out of fire, and the theory itself is built upon the same foundational idea as string theory, that our familiar four-dimensional universe is a membrane or brain, floating within a higher dimensional space known as the bulk. Imagine our entire cosmos, all of space and everything in it, as a gigantic, flat sheet of paper. Now imagine another universe, another sheet of paper, floating on a parallel plane in a higher dimension. According to the ekpyrotic model, these two brains could be drawn together by gravity across this hidden bulk dimension, eventually colliding with unimaginable force. That collision would release a colossal amount of energy, flooding our brain with radiation and matter, and effectively creating what we observe as the hot, dense state of the Big Bang. In this view, the Big Bang wasn't the absolute beginning. It was just the most recent reset button in an endless cycle of collisions. This elegant setup solves several of the most puzzling issues with the standard Big Bang model. One of the biggest mysteries is why the universe is so incredibly flat and uniform on the largest scales. The standard model requires a period of hyper-fast inflation to smooth everything out, a process that works but can feel like a necessary addition to fix the theory. The ekpyrotic model naturally produces a flat and smooth universe without needing a separate inflationary epoch. As the two brains move toward each other in the bulk, they naturally flatten and smooth out any wrinkles or imperfections from the previous cycle. By the time they collide, they are perfectly flat and parallel, resulting in a universe that is born inherently uniform, with the homogeneity we see in the cosmic microwave background baked directly into its creation. Furthermore, this model provides an elegant mechanism for generating the seeds of all cosmic structure. The quantum fluctuations that eventually became galaxies aren't stretched from tiny jitters during inflation, but are instead imprinted by the quantum mechanical vibrations of the brains themselves as they approach each other. The slight ripples and waves on the surface of these colliding membranes get translated into the tiny variations in density that gravity would later amplify into stars, galaxies, and the vast cosmic web. The pattern is not born from a random quantum fluctuation, but from the dynamic interaction of these colossal cosmological objects. The most profound implication of the ekpyrotic model is its vision of a cyclical, potentially eternal universe. After the collision, the brains bounce off each other and move apart, each now filled with the hot, dense plasma of a new universe. Each brain then expands and cools, much like our universe does now, forming galaxies and stars over billions of years. But eventually, the mysterious force of dark energy, which in this model could be the gentle tug of the other brain, will weaken. The expansion will halt, reverse, and the two brains will be drawn together once more across the bulk, setting the stage for the next collision and the next Big Bang. This cycle of creation and destruction could have been repeating forever, with no ultimate beginning and no final end. Our entire cosmic history is just one chapter in an endless story, a single breath in an eternal cosmic rhythm. It offers a powerful and poetic alternative to the standard narrative of a single, finite universe with a definitive start and a cold, lonely demise, suggesting instead that the cosmos is engaged in a perpetual dance of death and rebirth. Yet for all its success and explanatory power, the CMB map holds a few stubborn mysteries that refuse to be easily explained. Anomalies that some scientists believe could be cracks in our standard model or even hints of something far grander. The most famous of these is a peculiar alignment jokingly nicknamed the axis of evil. When scientists analyzed the pattern of fluctuations, they expected to find a random, isotropic distribution, noise that looked the same in every direction with no preferred axis or special point in space. This cosmological principle is a cornerstone of modern astronomy, but the data revealed something else entirely. Several large-scale features in the CMB appear to be oddly aligned with the plane of our own solar system and the direction of the Earth's motion through space. It's as if the universe's birth cry has a faint but detectable fingerprint of our own local cosmic address, which makes absolutely no sense. It would be like finding your own childhood fingerprints on the foundation stones of an ancient pyramid you're just now excavating. This bizarre alignment is considered an anomaly because it suggests a violation of the Copernican principle, the idea that we do not occupy a special or privileged place in the universe. The axis of evil remains a persistent thorn in the side of cosmology. It could be a subtle systematic error in the data processing, an unrecognized foreground effect from our own galaxy, or it could be a genuine, profound clue that our understanding of the universe's largest scales is incomplete. Some more speculative theories suggest it could be evidence of a pre-Big Bang structure, a relic of a previous cosmic cycle, or even a gravitational imprint from a neighboring universe in a vast multiverse, a cosmic bruise left by a collision we can barely perceive. While most cosmologists believe a more conventional explanation will eventually be found, this anomaly serves as a powerful reminder that our map of the infant universe, for all its detail, may still be hiding extraordinary secrets. But while we explore the grand architecture of space-time and the mysteries of cosmic origins, we must also turn our gaze to a question that feels infinitely closer to home. What if the patterns of the cosmos don't just shape galaxies and physical laws, but also life itself? This brings us to a profound and captivating family of ideas known as biological universe theories, which propose that the emergence and spread of life might not be a random, isolated accident on one lucky planet, but a natural and perhaps even inevitable cosmic process woven into the fabric of the universe. One of the most ancient and alluring ideas in this category is panspermia, the hypothesis that life, or its fundamental building blocks, is not confined to a single world but is distributed throughout space, hitching rides on asteroids, comets, and cosmic dust. The concept isn't new. The Greek philosopher Anaxagoras spoke of life seeds scattered throughout the universe. Modern panspermia comes in several forms. There's lithopanspermia, which suggests that microorganisms could be encased in rocks blasted off a planet's surface by a meteor impact, journeying through space in a protective rocky shell for millions of years, eventually landing on a fertile new world to seed it with life. We have compelling evidence that rocks from Mars have landed on Earth, so the mechanism is certainly plausible. Then there's the more radical directed panspermia, famously proposed by Francis Crick and Leslie Orgel, which playfully suggests that life on Earth could have been intentionally seeded by an advanced extraterrestrial civilization. While this remains highly speculative, the core idea of panspermia challenges our Earth-centric view of biology, suggesting that life could be a shared cosmic heritage, a single spark that has jumped from one celestial campfire to another, potentially igniting a chain of living worlds across the galaxy. This leads to a fascinating and deeply related question. If life did arise independently in multiple places, or even if it was spread from a common source, would it look anything like us? The theory of universal biochemistry suggests that the same fundamental physical and chemical constraints that shaped life on Earth would guide its development anywhere in the universe. The elements of life, carbon, hydrogen, oxygen, nitrogen, are among the most abundant in the cosmos and form stable, complex molecules with a versatility that other elements like silicon simply cannot match. Water, with its unique properties as a solvent and its abundance across interstellar space, is almost certainly the universal medium for biology. Even the specific molecular choices, like using DNA and RNA for information storage, might not be a frozen historical accident but the optimal solution to the problem of heredity and evolution. This doesn't mean we should expect to see bipedal humanoids on every Earth-like planet, but it does suggest that the underlying biochemical machinery, the use of amino acids, sugars, and nucleotides might follow a universal pattern. The laws of physics and chemistry could act as a universal architect, guiding evolution down convergent paths toward similar functional solutions, meaning eyes for seeing, wings for flying, and intelligence for problem-solving could be common themes in the cosmic story of life. Taking this idea of cosmic convergence to its ultimate conclusion, some scientists and philosophers ponder an even grander rhythm, that the development of life and perhaps even technological civilization might follow a predictable, quantifiable pattern. This is the realm of astrobiological theories that look for a potential equation for life, akin to the Drake equation but focused on the inevitable progression from simple chemistry to complex intelligence. The idea is that given the right conditions, a stable star, a planetary surface with liquid water, and sufficient time, the emergence of self-replicating molecules might be a near certainty, driven by the fundamental tendency of matter to organize under energy flow. From there, natural selection would take over, a powerful and unstoppable algorithm that inevitably leads to greater complexity and adaptation. This view sees evolution not as a series of lucky breaks, but as a predictable, directional process in a stable environment. Intelligence and technology, from this perspective, could be seen as an almost inevitable outcome of this relentless evolutionary pressure to better perceive, manipulate, and survive within one's environment. In this breathtaking vision, the universe might not just be hospitable to life, it might be pregnant with it, inherently biased toward the emergence of consciousness as a natural part of its unfolding story. The cosmos may not merely contain life as a rare jewel, but may be fundamentally alive, with biological processes being as natural and widespread as the formation of stars. This uncanny feeling that our universe seems suspiciously well-suited for our existence leads us directly to one of the most profound puzzles in all of science, the Goldilocks principle in cosmology. It's the startling realization that many of the fundamental constants and conditions of our universe aren't just arbitrary numbers. They appear to be exquisitely fine-tuned to a breathtakingly precise degree, falling within an incredibly narrow range that allows for the existence of stars, planets, and ultimately, life. If these values were even slightly different, by a fraction of a percent in some cases the cosmos as we know it would be impossible. It's as if the universe's dials were set not randomly but deliberately to a setting that is just right. Consider the force of gravity described by the gravitational constant. If this force were significantly stronger, stars would burn their fuel far too quickly and fiercely, collapsing into black holes before life could ever have a chance to evolve on any orbiting planets. A more powerful gravity would cause the universe to recollapse on itself in a fiery big crunch almost immediately after the Big Bang. But if gravity were even a little bit weaker, it wouldn't be strong enough to pull matter together to form stars and galaxies in the first place. The cosmic matter would simply drift apart into an ever-diffusing, thin, and lifeless haze. The same delicate balance is found in the strength of the strong nuclear force, which holds the nuclei of atoms together. If it were slightly weaker, simple hydrogen would be the only element in existence, as protons could never bind together to form the heavier elements essential for planets and life. Yet if it were stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for long-lived stars like our Sun. The universe is perfectly poised between these two catastrophic extremes. This fine-tuning extends far beyond just the forces. The initial conditions of the Big Bang itself were set with an almost miraculous precision. The density of the early universe was balanced on a razor's edge. If the expansion rate had been minutely slower, the universe would have collapsed back in on itself under its own gravity. If it had been even a fraction faster, matter would have flown apart too rapidly to ever coalesce into galaxies. The cosmological constant, which drives the accelerating expansion of the universe, is fine-tuned to an almost absurd degree of accuracy, to within 1 part in 10 to the power of 120. This is a number so incomprehensibly precise that it has been called the worst prediction in the history of physics. Faced with this astonishing array of cosmic coincidences, scientists are forced to ask the obvious question, why? How do we explain this incredible luck? There are 3 main families of answers to this profound puzzle, each with staggering implications. The first, and currently most popular among physicists, is the multiverse explanation. This solution applies the ultimate form of the anthropic principle. If an infinite or near infinite number of universes exist, each with its own random set of physical constants and laws, then it is no longer surprising that we find ourselves in one of the rare, life-permitting universes. We are the inevitable outcome of a cosmic lottery with an almost infinite number of tickets. In this view, there is no fine-tuning, only a colossal selection effect. We shouldn't marvel that the universe is suited for us. We should simply recognize that we could not exist in any of the inhospitable ones. The Goldilocks conditions aren't a puzzle to be solved, but a fact of our particular location in a vast and varied cosmic landscape. The second explanation is perhaps the most intuitive for many, some form of teleology or design. This argument posits that the constants are fine-tuned because they were set that way, either by a divine creator or by some unknown cosmic intelligence. This perspective suggests the universe had a purpose or a goal from the very beginning, and the laws of physics were intentionally calibrated to make complexity and consciousness possible. While this idea lies outside the realm of testable science for many, it remains a powerful intuitive response to the mystery. It resonates with the feeling that such breathtaking precision cannot be merely accidental, that it points toward an underlying purpose or mind behind the cosmos. The third, and for scientists perhaps the most compelling, possibility is that we simply haven't discovered the deeper physical principle yet. The apparent fine-tuning may be an illusion created by our incomplete knowledge. Just as Einstein's theory of relativity revealed that gravity was not a mysterious force but the curvature of spacetime, a future theory of everything might show that these constants are not free parameters to be set by chance, but are actually the only possible values locked in place by a deeper, more fundamental law we have not yet uncovered. They might be the inevitable outcome of a single, elegant equation, making our universe not one lucky possibility in a multiverse, but the only universe that could logically exist. The search for this deeper theory is the holy grail of modern physics, driven by the hope that the Goldilocks enigma is not a question of probability, but a signpost pointing toward a more profound and unified understanding of reality itself. But for all its mathematical elegance and predictive power, quantum mechanics leaves us with a deeply unsettling question about the world we actually live in. If, at its foundation, reality is a blurry cloud of probabilities and potentialities, a realm where particles have no definite properties until they are observed, then why does our everyday world feel so solid, so stable, and so objective? Why don't chairs and tables and the moon itself dissolve into quantum fuzziness when we're not looking at them? This chasm between the weird quantum underworld and the dependable classical reality we experience is known as the quantum measurement problem, and one of the most compelling solutions to it is a theory called quantum Darwinism. This idea proposes that the definite reality we all agree upon isn't dictated by a mysterious conscious observer, but emerges through a process strikingly similar to natural selection, where the fittest quantum states are the ones that get copied and broadcasted to the world. To grasp this, let's revisit the core weirdness of quantum mechanics. Think of an electron. Before you measure its spin, it exists in a superposition of all possible spins. It's both up and down simultaneously. The act of measurement, according to the traditional Copenhagen interpretation, somehow collapses this wave of possibilities into one definite outcome. But this always leads to the thorny question: what counts as a measurement? Is it a conscious human, a photographic plate, a single atom? This is a deeply unsatisfying place for physics to end. Quantum Darwinism, developed by theorists like Wojciech, offers a way out. It suggests that the collapse isn't a magical event triggered by observation, but a physical process driven by the environment. Here's how it works. Imagine that solitary electron in its fragile superposition. Now, imagine it's not isolated in a perfect lab, but out in the real world, surrounded by trillions of photons of light, air molecules, and dust particles. This is its environment. The key insight is that this electron doesn't just interact with one thing at a time. It constantly bumps into and interacts with countless particles in its surroundings. And with every single one of these interactions, the electron imprints information about its state onto the environment, but it doesn't imprint information about its entire fuzzy wave function. It's incredibly selective. Only certain quantum states, the ones that are robust and stable and don't get easily perturbed by these interactions, are able to reliably leave a mark. These special states are called pointer states, and they are the quantum equivalent of a species perfectly adapted to its environment. This is where the Darwinian part comes in. The environment acts like a constant, selective pressure. Those pointer states are the fittest because they can survive the decoherence process, the rapid scrambling of quantum information that occurs when a system interacts with its surroundings. The fragile superpositions, the ones that are both up and down, are instantly destroyed by this decoherence. They are not stable enough to leave a consistent imprint. But the pointer states are. They are repeatedly copied, replicated, and spread throughout the environment. A single photon bouncing off the electron carries a tiny bit of information about its spin. Then another photon does the same, and another, and another. Soon, countless particles in the environment are all carrying the same, consistent information. The electron's spin is up. This proliferation of information is the quantum version of a successful gene being spread throughout a population. So, why do we perceive a definite reality? Because to find out anything about the electron, you and I don't need to directly interact with it. We simply sample a small part of its environment. We intercept a few of those photons that have been bouncing around, and since the environment has been flooded with redundant copies of the same information, spin up, everyone who goes to measure it will find the same thing. We all agree on the objective reality of the electron state, not because some grand collapse happened, but because we are all independently reading from the same cosmic data stream, a stream that has been amplified and broadcasted by the environment itself. The role of the observer is demoted from a mysterious collapse causer to a mere information gatherer, just another system interacting with the environment. The moon is there when nobody looks because it is constantly interacting with sunlight, cosmic rays, and the solar wind, which tirelessly and redundantly copy information about its position and state into the fabric of space, creating a consistent story that any observer can access. Quantum Darwinism tells us that the classical world emerges not from a single act of observation, but from the relentless, selective copying of the most stable quantum information, weaving the definite tapestry of reality from the quantum blur through a billion tiny interactions every second. But this delicate dance of quantum information faces its ultimate challenge in the most destructive environments imaginable, plunging us into a paradox that threatens to unravel the very foundations of physics. This is the black hole information paradox, a fierce battle between the two great pillars of modern science, general relativity and quantum mechanics, that centers on a deceptively simple question: when something falls into a black hole, is the information that describes it lost forever? For decades, this puzzle has divided physicists, with the answer hinging on a seemingly innocuous prediction from Stephen Hawking that these cosmic monsters should slowly evaporate into nothingness. The story begins with Hawking's stunning realization in the 1970s that black holes aren't completely black. Due to weird quantum effects happening right at the edge of the event horizon, they should actually emit a faint glow of radiation, now famously known as Hawking radiation. Here's how it works. The quantum vacuum isn't empty. It's a seething sea of virtual particle pairs constantly blinking in and out of existence. Normally, these pairs annihilate each other almost instantly. But if this happens right at the event horizon, one particle might fall into the black hole while the other escapes into space. To conserve energy, the particle that falls in must have negative energy, which effectively reduces the black hole's mass. The escaped particle becomes real radiation, carrying energy away from the black hole. Over unimaginable eons, this process causes the black hole to slowly shrink and eventually vanish completely. This is where the paradox erupts. The Hawking radiation that escapes is completely random and thermal. Its properties depend only on the black hole's mass, charge, and spin. It contains no information whatsoever about the specific things that fell in, whether it was a star, a spaceship, or a library of encyclopedias. According to the strict rules of quantum mechanics, information can never be truly destroyed. It can be scrambled and hidden, but it must always, in principle, be recoverable. This is a fundamental tenet called unitarity. If you could magically reverse time, you should be able to trace every particle back to its origin. But if a black hole evaporates into a featureless puff of random radiation, the information about everything it ever consumed is seemingly erased from the universe. This presents a catastrophic choice. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and our understanding of black holes is deeply flawed. For a long time, Hawking himself believed information was truly lost, famously making a bet against other physicists who argued it must be preserved. This proposed violation of quantum law was so unsettling it was dubbed by John Preskill the black hole information problem. The potential ramifications are staggering. If information can be lost, it breaks the predictability that is the bedrock of physics and throws causality into chaos. Thankfully, Hawking later changed his mind, but the question remained: if information is saved, how does it possibly escape? One of the most elegant solutions brings us back to the holographic principle. The information isn't stored deep inside the black hole's mysterious interior. It's encoded on its surface, painted onto the event horizon in Planck-scale bits. Just as a hologram can store three-dimensional information on a two-dimensional surface, the entire description of everything that falls in could be preserved on the black hole's boundary. When Hawking radiation is emitted, it isn't random. It subtly interacts with and carries away tiny bits of this encoded information, like a slow, careful data transmission that eventually returns all the scrambled information to the universe as the black hole evaporates. The information was never truly lost, just incredibly difficult to decode. A far more violent and radical solution is the black hole firewall paradox. If information is to be saved, some theorists argue that the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it must be a blazing wall of high-energy particles, a firewall that instantly incinerates anything crossing it. This firewall would resolve the information paradox by creating a clear boundary where information is scrambled and emitted, but it does so by violating Einstein's equivalence principle, which states that an observer falling into a black hole should experience nothing special at the horizon. You can't have both a smooth entry and preserved information. You must choose, and the firewall hypothesis chooses information preservation at the cost of a dramatic rewrite of physics at the horizon. This paradox forces us to confront the limits of our current theories and points the way toward the need for a theory of quantum gravity. The fate of information in a black hole is likely tied to the very nature of spacetime itself, suggesting that our concepts of locality and reality break down in such extreme environments. The resolution, whatever it may be, promises to reveal a deeper, more unified truth about our universe, showing us that even its most terrifying voids might adhere to a hidden logic that keeps the cosmos computationally consistent from the smallest quantum fluctuation to the largest gravitational well. Yet if black holes present a terrifying end for information, another theory offers a far more grand and poetic vision of eternity, one where the end of time is not a cold silence but a beautiful return to a new beginning. This is Sir Roger Penrose's breathtakingly audacious conformal cyclic cosmology, a theory that proposes our universe is not the first and only one, but merely one episode in an endless cycle of death and rebirth, where the distant, empty future of one universe becomes the hot, dense Big Bang of the next. It's a vision that elegantly sidesteps the need for a singular, inexplicable beginning, suggesting instead that the cosmos is immortal, engaged in an infinite dance of expansion and renewal. To grasp this radical idea, we need to consider the ultimate fate of our universe as dictated by the relentless acceleration of dark energy. In a trillion years, all stars will have long since burned out. Galaxies will have evaporated, their stars escaped into the intergalactic void. Eventually, even the stellar remnants, white dwarfs, neutron stars, and planets will decay through quantum processes, and black holes themselves will slowly evaporate away via Hawking radiation. What remains is a universe that is nearly, but not perfectly, empty. It is filled only with an incredibly dilute sea of radiation and a handful of massless or nearly massless particles, all drifting further and further apart in an ever-expanding, ever-cooling emptiness. This seems like the most desolate and final state imaginable, a true end of everything. But Penrose saw something else in this bleak landscape. He recognized that in this state of extreme dilution and expansion, the universe undergoes a profound transformation. The concept of distance and time, so crucial to our current physics, loses all meaning. When there are no massive particles left, there is no way to build a clock or a ruler. The universe becomes effectively timeless and scale-less. In this strange, stretched-out state, its geometry becomes what mathematicians call conformally invariant. It has no defined scale, and its shape is all that remains. This is the magical key to Penrose's cycle. In a conformally invariant universe, you can mathematically rescale everything. You can essentially shrink this vast, cold, empty universe down to a tiny, hot, dense point without changing its fundamental geometric relationships. And what does a tiny, hot, dense point sound like? It sounds exactly like the initial singularity of a Big Bang. Penrose's brilliant insight was that the conformal geometry of the infinitely expanded, empty future of one universe is mathematically identical to the conformal geometry of the zero-size, high-energy beginning of another. The end of one eon, as he calls each cycle, becomes the beginning of the next. There is no singularity separating them. It is a smooth, continuous transition where the universe, in a sense, forgets its scale and is reborn. The entire infinite future of our universe can be conformally transformed into the Big Bang of the next. This creates an endless, infinite chain of eons, each with its own history of stars, galaxies, and perhaps life, all connected in an eternal loop where time itself is recycled. But a theory this beautiful needs more than mathematical elegance. It needs observational evidence. Penrose and his colleague Vargursadian proposed a stunning and specific prediction. If a previous eon existed before our own Big Bang, and it was populated by supermassive black holes that eventually collided and merged, these cataclysmic events would have sent immense gravitational waves rippling through the fabric of space-time. In the conformal transition to our new eon, the energy from these waves would be imprinted onto the new universe's earliest moments. This imprint would manifest in the cosmic microwave background, the fossilized light from our own Big Bang, as a series of bizarre, concentric circular patterns. These circles would be regions of slightly lower temperature variance than the surrounding CMB, the ghostly echoes of black hole collisions from a universe that existed before time as we know it began. Incredibly, Penrose and Gursadian claim to have found precisely these patterns in the data from the WMAP and Planck satellites. Their analysis pointed to dozens of these concentric rings, which they argued could not be explained by the standard inflationary model and were a direct signature of a pre-Big Bang universe. The scientific community met this claim with intense skepticism. Many other teams analyzed the same data and argued that the patterns Penrose identified were simply random statistical fluctuations, the kind you would expect to find in any complex dataset. They pointed out that the standard inflationary model already predicts a certain distribution of hot and cold spots, and that the alleged circles did not stand out as statistically significant anomalies against this background noise. The debate became a fierce, technical battle over data analysis methods and significance thresholds. Despite the controversy, the sheer power of Penrose's idea remains captivating. It offers a profound and elegant alternative to both the single universe model and the inflationary multiverse. It requires no new, unobserved physics like inflation. It works entirely within the known framework of general relativity and thermodynamics, pushing them to their most profound conclusions. It provides a natural explanation for the low entropy state that launched our universe's arrow of time. The state was low entropy because it was the transformed, high energy beginning of a new cycle, not a random fluctuation. Most poetically, it suggests that the universe is neither created nor destroyed, but exists in a state of perpetual transformation, where every ending seamlessly blossoms into a new beginning, weaving an infinite tapestry of cosmic stories across eons of time we can scarcely imagine. Gravity is the force that holds the cosmos together, sculpting galaxies and guiding planets in their eternal dance. It feels powerful to us, anchoring us to our world. But to a physicist, gravity is astonishingly, puzzlingly feeble. This glaring weakness is one of the most profound unsolved puzzles in fundamental physics, a mystery known as the hierarchy problem. To understand just how weak gravity is, consider a simple experiment. Lift a paperclip with a small fridge magnet. That tiny magnet, using the electromagnetic force, is effortlessly overpowering the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. The numbers are even more staggering. The gravitational force is about 1,000 trillion times weaker than the electromagnetic force. Why is there such a colossal difference in strength between these fundamental forces? This isn't a minor detail. It's a screaming clue that our understanding of the universe is missing a major piece of the puzzle. The problem becomes even sharper when we look at the Higgs boson. The mass of the Higgs is directly tied to the energy scale at which the weak nuclear force operates, a scale that is itself thousands of times lower than the Planck scale, the ultra-high energy level where gravity is expected to become strong. This creates a hierarchy or a vast desert between these two energy scales, and according to our current equations, this huge gap is incredibly unstable. Quantum fluctuations should constantly be pushing the mass of the Higgs, and by extension the weak scale, up toward the enormous Planck scale, effectively making the Higgs astronomically heavier than it actually is. For our universe to have the particles and forces we see, an absurdly precise and unnatural cancellation between these quantum corrections must occur. It's as if you tried to balance a pencil perfectly on its point on a windy day. It's possible in theory, but it would require unimaginably fine-tuning the initial conditions. Most physicists believe such perfect fine-tuning is a sign that we are missing a deeper mechanism, a new symmetry or principle that naturally protects the Higgs mass and explains this vast gulf. One of the most elegant and sought-after solutions is a concept known as supersymmetry, often shortened to SUSY. This beautiful theory proposes that for every known particle in the Standard Model, every electron, quark, and photon, there exists a hidden super-partner particle. For the electron, there would be a selectron, for the quark, a squark, for the photon, a photino. These super-partners would have different quantum properties, most notably their spin. The magic of supersymmetry is that the quantum contributions of a particle and its super-partner to the Higgs mass would be exactly opposite. They would cancel each other out perfectly, naturally stabilizing the Higgs mass and solving the hierarchy problem without any need for miraculous fine-tuning. It's a stunningly graceful solution. Furthermore, supersymmetry provides an excellent candidate for dark matter. The lightest supersymmetric particle could be stable, neutral, and abundant, exactly matching the properties we observe. For decades, physicists were confident they would find evidence for supersymmetry at the Large Hadron Collider. Yet, so far, these superpartners have remained elusive. Their continued absence suggests that if supersymmetry is real, it must be operating at a much higher energy scale than we had hoped, making it a less natural solution to the problem it was designed to fix. The dream of supersymmetry is still alive, but it's waiting for a new generation of even more powerful experiments. Another mind-bending solution to the hierarchy problem doesn't try to strengthen the other forces to match gravity's weakness, but instead proposes that gravity only appears weak because we're not sensing its full strength. This is the idea that gravity, and only gravity, can leak into extra-spatial dimensions beyond the three we experience. Imagine our three-dimensional universe is a vast, impossibly thin membrane, a brain, floating within a higher dimensional space called the bulk. The particles of the Standard Model, the stuff that makes up you, me, and everything we see are stuck to this brain, like beads of water on a shower curtain. They cannot leave, but the graviton, the hypothetical particle that carries the gravitational force, is different. It is not confined to our brain. It can propagate freely into the extra dimensions. In this scenario, gravity isn't intrinsically weak, it's just diluted. Its force is spread out across all the dimensions, and we in our three-dimensional world only experience a tiny, faint sliver of its true strength, like feeling only a small part of a wave that's spreading out in all directions. This brilliant idea, pioneered by theorists like Nima Arkani-Hamed, Savas Dimopoulos, and Georgi D. Volley, allows the true fundamental scale of gravity to be much, much lower, potentially even down to the weak scale. The vast hierarchy between the forces vanishes. It was an illusion created by geometry. This model makes a dramatic and testable prediction. If these extra dimensions are large enough, perhaps on the scale of a fraction of a millimeter, then at incredibly tiny distances, gravity should stop following its familiar inverse square law and become dramatically stronger. Experiments are actively searching for this deviation, using exquisitely sensitive devices to measure the gravitational force between objects placed mere microns apart. Another version of this idea, the Randall-Sundrum model, proposes a warped extra dimension where the weakness of gravity is explained by the geometry of the universe itself being sharply curved. Exploring these possibilities pushes the boundaries of what we consider possible, suggesting that the hidden pattern of force strengths might be a direct map of the universe's true higher dimensional shape. The hierarchy problem forces us to confront the possibility that the constants of nature we measure are not fundamental truths, but emergent properties shaped by the deeper architecture of reality. The incredible weakness of gravity might be the most important clue we have, a direct signal that our universe is part of something far larger and more complex. It tells us that the patterns we perceive are often just shadows, and that the true nature of the cosmos might be hidden in dimensions we cannot see or woven from symmetries we have not yet discovered. Solving this puzzle wouldn't just answer a technical question in physics, it would open a window into the deepest layers of existence, revealing why our universe is built the way it is. But if the hierarchy problem reveals gravity's puzzling weakness, our next theory reveals a hidden strength simmering in the void of so-called empty space. We've been taught that a vacuum is nothingness, a complete absence of matter and energy, but quantum physics paints a radically different picture. It reveals that the vacuum is not empty at all, but is instead a seething, bubbling, dynamic arena, a quantum foam teeming with fleeting particles and a boundless, underlying energy that might just hold the key to the universe's greatest mysteries. This is the realm of the quantum vacuum and zero-point energy, a background hum of existence so fundamental that it might be the canvas upon which all of reality is painted. To understand this, we need to revisit Werner Heisenberg's famous uncertainty principle. This cornerstone of quantum mechanics states that on the tiniest scales, there is a fundamental limit to what we can know. You cannot precisely know both a particle's position and its momentum at the same time, but this principle isn't just about measurement, it's about reality itself. It implies that a quantum system can never truly settle into a state of perfect, dead stillness. There is always a residual jitter, a fundamental uncertainty. Now apply this to the concept of nothingness. For there to be truly nothing, a region of space would have to have exactly zero energy for an infinite amount of time. The uncertainty principle forbids this. Even at absolute zero temperature, the lowest energy state possible, a system must still possess a tiny, irreducible amount of energy. This is the zero-point energy, the energy that remains when everything else is taken away. It is the cost of admission for existing in a quantum universe. This isn't just a theoretical curiosity, it has observable consequences. The most famous is the Casimir effect, a stunning experimental validation of this quantum seething. Imagine two plain, uncharged metal plates placed incredibly close together in a perfect vacuum, only a few nanometers apart. Classical physics would say nothing should happen between them. But in the quantum world, the space between the plates is restricted. Only certain wavelengths of virtual particles can flicker into existence in that narrow gap. Outside the plates, any wavelength can appear. This creates a pressure imbalance, the greater number of virtual particles pushing on the outside of the plates than on the inside causes the plates to be gently but measurably pulled together. It's a direct physical manifestation of the zero-point energy of the vacuum, a force generated entirely by the restless activity of nothingness. This leads us to one of the most profound connections in all of cosmology. This vacuum energy, this zero-point energy of empty space, is the leading candidate for the mysterious dark energy that is accelerating the expansion of the universe. The cosmological constant that Einstein introduced and then discarded might very well be this energy. There's just one enormous and frankly embarrassing problem. When physicists try to calculate how much energy this quantum vacuum should contain by summing up all the contributions from every possible quantum field, the number they get is absurdly large. We're talking about a value that is 10 to the power of 120 times larger than the value we actually observe from the acceleration of the cosmos. This is the largest discrepancy between theory and observation in the entire history of science. It means either our understanding of the quantum vacuum is catastrophically wrong, or some unknown, miraculous cancellation is happening with a precision that is almost impossible to comprehend. This vacuum energy catastrophe remains one of the deepest unsolved puzzles in physics, a glaring signpost that we are missing a fundamental piece of the puzzle. Beyond this cosmic role, some theorists have proposed an even more radical idea, that this quantum vacuum is not just a backdrop, but an active participant in the universe, potentially encoding a hidden pattern that connects all things. The concept of a Dirac sea, or the ideas behind quantum field theory, suggest that what we perceive as particles are merely excitations or waves in these underlying fields that fill all of spacetime. The electron field, the quark field, the electromagnetic field, these are the true fundamental entities. The vacuum is the default state of these fields, and particles are just tiny vibrations within them. In this view, the entire universe is an ocean of energy, and particles are like waves on its surface. This suggests a profound interconnectedness. Every electron in the universe is a ripple in the same electron field. The vacuum is the medium that connects them all. This leads to speculative but fascinating ideas that the zero-point field could act as a cosmic memory or an implicate order, as physicist David Bohm suggested. The countless interactions between particles could be recorded as subtle disturbances in the vacuum, a permanent, if faint, imprint on the fabric of spacetime. The patterns of the universe, from the spin of a galaxy to the firing of a neuron, might leave their trace in this fundamental medium. While this veers into the frontiers of theoretical physics, it highlights a shift in perspective. The vacuum is not a passive stage, but a dynamic and potentially informative plenum. It is the richest, most complex thing imaginable, the source from which all particles, forces, and perhaps even the patterns of reality itself continuously emerge and dissolve back into. We are not isolated beings moving through a void. We are transient patterns, intricate whirlpools of energy, sustained by and connected through the boundless, humming energy of the quantum vacuum. But this strange, ghostly connection between particles forces us to ask an even deeper question about the very nature of reality. What if every time a quantum event has multiple possible outcomes, the universe doesn't choose one? What if it chooses all of them, with each possibility playing out in its own separate, fully realized branch of existence? This is the stunning and mind-bending proposal of the many worlds interpretation of quantum mechanics, a theory that replaces the mysterious collapse of the wave function with an infinitely branching, ever-expanding multiverse where every possible version of history is not just a probability, but an actuality. The story begins in the 1950s with a brilliant and unorthodox graduate student named Hugh Everett Roman III. he was deeply troubled by the standard Copenhagen interpretation of quantum mechanics, which required a vague and undefined measurement to collapse probabilities into a single reality. Who or what qualifies as an observer, a cat, a bacteria, a photon? Everett found this dualism, where quantum rules govern the tiny world but a separate set of classical rules magically takes over upon observation, to be arbitrary and unscientific. He proposed a radical alternative. What if the wave function never collapses at all? What if it just continues to evolve smoothly and deterministically, following Schrödinger's equation forever? The problem, of course, is that we only ever see one outcome. Everett's genius was to realize that the other outcomes don't disappear. They simply decohere, becoming separate and non-interacting parts of a much larger reality. Imagine you're about to perform the famous Schrödinger's cat experiment. You place the cat in the box with the radioactive atom and the vial of poison. According to quantum rules, the atom is in a superposition of both decayed and not decayed. This means the cat is in a superposition of both alive and dead. Now you open the box to look. In the Copenhagen view, your observation collapses the whole system, and you find either a very relieved or a very deceased cat. But in the many worlds view, your act of observation doesn't cause a collapse. Instead, it causes a branching. The universe splits into two distinct and equally real branches. In one branch, you open the box and find a living cat. In the other branch, a completely separate version of you opens the box and finds a dead cat. Both events happen. Both yous are real, but they are now forever isolated from each other, each experiencing their own unambiguous outcome. There is no single privileged reality. There are only perspectives within an endlessly forking tree of possibilities. This resolves the measurement problem with breathtaking elegance. There is no longer a need for a special collapse rule or a mysterious role for consciousness. The wave function just is, and it contains all possibilities. What we perceive as the random, probabilistic nature of quantum events is simply our subjective experience of being a particular branch in this infinite tree. From a God's eye view outside the universe, everything that can happen does happen somewhere. The probability of finding yourself in a branch where the cat is alive is exactly 50%, which matches the quantum prediction. The randomness is an illusion created by our limited, single-branch perspective. The implications of this are enough to make your head spin. It suggests that every quantum event, no matter how small, creates new universes. Every time an atom decays, every time a photon is reflected or transmitted, the cosmos bifurcates. The number of parallel worlds is not just large, it is truly infinite, being created every nanosecond. In some of these worlds, your every dream has come true. In others, your every nightmare is reality. There is a universe where you never met your partner, another where you took that job overseas, and another where a stray quantum fluctuation prevented your ancestors from ever meeting. The tapestry of reality is not a single thread but an unimaginably vast and complex fabric, weaving together every possible permutation of every possible event. This raises a profound and personal question. What does this say about you? The many worlds interpretation suggests that your conscious experience is not a continuous, unbroken stream, but a single path being traced through this infinite multiverse. The you watching this video is just one version of countless others. Your sense of free will might be the experience of navigating this branching structure, making choices that determine which branch you continue to inhabit, even as other versions of you travel down the roads not taken. It is a vision of reality that is at once terrifying in its scope and profoundly liberating in its possibilities, suggesting that every potentiality is realized, every story is told, and the cosmos is infinitely richer and more strange than we could ever have imagined. While we've been exploring the cosmic microwave background as the oldest light in the universe, there's an even older, far more elusive fossil permeating all of space. one that has been streaming through you and everything around you since the dawn of time. This is the cosmic neutrino background, a faint sea of nearly massless particles born in the very first second of the universe's existence. If the CMB is a baby picture of the cosmos at 380,000 years old, the CNB is a cryptic ultrasound from when the universe was barely 1 second old, offering a direct window into conditions so extreme that not even light can directly testify to them. To understand the significance of these ghostly particles, we need to rewind the cosmic clock even further back than the moment the CMB was set free. Just 1 second after the Big Bang, the universe was an unimaginably dense and hot soup of fundamental particles, a seething plasma where protons and neutrons were just beginning to form. At this early stage, photons, particles of light, were not free to travel. They were constantly bouncing off and interacting with free electrons trapped in a chaotic dance. But neutrinos are different. They are the ultimate introverts of the particle world, interacting with matter only through the weak nuclear force and gravity. This makes them incredibly antisocial. Because of this, as the universe cooled to around 10 billion degrees Kelvin at that 1 second mark, neutrinos suddenly found they could stop interacting with other particles. They decoupled, flying free from the primordial plasma and streaming across the universe, largely untouched and unchanged for the next 13.8 billion years. This moment of neutrino decoupling created a background radiation field far more ancient than the CMB, a snapshot of the universe in its fiery infancy. Detecting this fossil, however, is a monumental challenge precisely because neutrinos are so elusive. Trillions of them from the cosmic neutrino background are passing through your body every second, and almost all of them travel through the entire Earth without a single interaction. They are nicknamed ghost particles for a reason. This makes capturing one of these relic neutrinos an experiment of almost unimaginable difficulty. We can't simply build a giant telescope to see them. We have to catch them in the act of very rarely bumping into something. Current technology is not yet sensitive enough to directly detect these specific 1 second old neutrinos. Their energy is incredibly low, having been stretched and cooled by the expansion of the universe to a temperature of just about 1.95 degrees above absolute zero, even colder than the CMB. The hunt for the CNB is the next great frontier in observational cosmology, pushing our engineering and scientific creativity to the absolute limit. Future proposals involve building colossal, ultra-cold detectors filled with exotic materials like liquid helium or heavy hydrogen, placed deep underground to shield them from other radiation, all waiting for the once-in-a-lifetime ping that might signal a collision with a neutrino from the dawn of time. Why go to such extraordinary lengths? Because the information encoded in this neutrino background is utterly priceless. These particles are messengers from an era before the formation of light elements, before the formation of atoms, even before the formation of protons and neutrons as we know them. They carry an unaltered record of the universe's density and temperature fluctuations from its very first second. By mapping the CNB, we could test our theories of the Big Bang itself with unprecedented precision. It could provide direct evidence for the process of neutrino decoupling and help us pin down the exact properties of neutrinos, such as their exact masses and whether they are their own antiparticles. Furthermore, because these neutrinos began streaming freely before the photons of the CMB, their pattern on the sky would be different. They would show us the primordial universe at a higher resolution, revealing the initial seeds of structure before gravity had even begun to amplify them into galaxies. Analyzing the subtle differences between the CNB map and the CMB map would be like comparing two photographs of the same person taken years apart, allowing us to trace the entire growth and evolution of cosmic structure from its absolute origin. Most intriguingly, the cosmic neutrino background could be the key to uncovering physics beyond our current understanding. The sheer number of these relic neutrinos is staggering. There are about 336 of them in every cubic centimeter of space, outnumbering even the photons in the CMB. This immense population means that even though each individual neutrino has a tiny mass, their collective gravitational influence could have played a crucial role in shaping how the largest structures in the universe, like the cosmic web of galaxies, formed and evolved. Their subtle pull may have acted as a kind of invisible scaffolding, guiding the collapse of matter in ways we are only beginning to model. By studying this effect, we might finally understand the precise hierarchy of neutrino masses and uncover whether these ghostly particles played a starring role in writing the hidden patterns of the cosmos, their faint whisper echoing through billions of years to shape the universe we see today. We've been exploring the hidden patterns of the cosmos, from the quantum foam at the smallest scales to the vast, branching multiverse of the many worlds interpretation. But there is another invisible force weaving through the fabric of reality, one that you can actually demonstrate with a simple refrigerator magnet: its magnetism. While we often think of it as a local phenomenon, something that makes compass needles point north or holds our shopping lists to the fridge, its influence is truly cosmic. The magnetic universe hypothesis proposes that magnetic fields are not a minor detail in the story of the cosmos. They are a fundamental and pervasive architectural feature, shaping the evolution of everything from the birth of stars to the colossal filaments of the cosmic web, and their origin might be one of the universe's oldest secrets. For a long time, astronomers considered magnetic fields to be something of an afterthought in cosmology, a secondary effect generated by moving plasma, like the dynamo in Earth's core that creates our protective magnetosphere. But as our telescopes and simulations have improved, we've discovered that magnetism is everywhere we look, and it is far stronger than anyone expected. Our own Milky Way galaxy has a magnetic field with lines of force tracing its spiral arms. Other galaxies have them too, often with fields thousands of times stronger than our own. These galactic fields are not just random, they are coherent, structured, and incredibly large-scale. But the real surprise came when we looked at the spaces between galaxies. Vast, tenuous clouds of gas known as galactic filaments, which form the threads of the cosmic web, also show evidence of magnetic fields. Even the immense voids, the emptiest regions in the universe stretching for hundreds of millions of light years, are not completely empty of magnetic influence. This omnipresence presents a monumental puzzle. How did such powerful and extensive magnetic fields form, and when did this happen? This is where the hypothesis splits into two fascinating camps, each with profound implications. The first is the primordial origin theory. This idea suggests that magnetic fields are not made by galaxies, but instead galaxies formed within them. The seed of these fields could have been generated in the extreme conditions of the very early universe, perhaps during a phase transition in the first fraction of a second after the Big Bang, or even during the period of cosmic inflation. In this scenario, the entire universe was briefly a perfect super-hot superconductor. As it expanded and cooled, tiny quantum fluctuations could have been stretched to cosmological sizes, imprinting a faint, primordial magnetic field across all of space. These fields would have been incredibly weak at first, but as the universe evolved and matter collapsed under gravity to form galaxies and clusters, these magnetic lines of force would have been squeezed and amplified, like a loose loop of string being pulled taut. This would explain why we see magnetic fields everywhere, because they were there from the very beginning, woven into the fabric of space-time itself as a fundamental feature of creation. The alternative and more traditional view is the astrophysical dynamo theory. This model argues that the first magnetic fields were indeed very weak, perhaps generated by the first stars and galaxies. As plasma, a hot, ionized gas where electrons are stripped from their atoms, moves through space, it can generate electrical currents. These currents, in turn, create magnetic fields. Once a tiny initial field exists, a dynamo effect can take over. The rotation of a galaxy, for instance, can twist and shear these magnetic lines, wrapping them up and amplifying them over millions of years, much like a simple hand-crank generator. This process is efficient and well understood on smaller scales. The challenge for the dynamo theory is explaining how the initial, weak seed fields were generated so uniformly across the entire cosmos, and how they were amplified quickly enough to account for the strong fields we see in very young, distant galaxies. It's a bit of a chicken and egg problem. You need a magnetic field to amplify a magnetic field. Regardless of how they started, the influence of these cosmic magnetic fields is undeniable and dramatic. They play a crucial role in the life cycle of stars. Within giant clouds of interstellar gas, magnetic fields provide a supporting pressure against the relentless pull of gravity. This magnetic support can slow down the collapse of a gas cloud, regulating the rate of star formation and potentially determining the final mass of a newborn star. Without magnetic fields, galaxies might have burned through their fuel in a frantic burst of star formation, leaving behind nothing but dead stars and darkness. Magnetic fields are also the universe's ultimate particle accelerators. When a star explodes as a supernova, the shockwaves can travel along magnetic field lines, accelerating charged particles like protons and electrons to nearly the speed of light, creating the cosmic rays that constantly bombard our atmosphere. The most dramatic effects are seen around supermassive black holes at the centers of galaxies, where magnetic fields can launch and collimate jets of material that travel for thousands of light years, pumping energy into the intergalactic medium and shaping the evolution of entire galaxy clusters. The true hidden pattern here is one of connection and influence. Cosmic magnetic fields act as an invisible skeleton, providing structure and channeling energy across the vastest distances. They govern the birth of stars, guide the cosmic rays, and control the feedback processes that regulate galaxy growth. The hunt to understand their origin is really a hunt for a deeper layer of cosmic order. If the fields are primordial, they are a direct relic from the universe's first moments, a fossil that could reveal new physics about inflation and the birth of spacetime. If they are purely astrophysical, then we are witnessing the incredible efficiency of a universal dynamo, a self-organizing process that emerges from the chaotic motions of plasma. Future telescopes designed to detect the faint polarization of light caused by these fields will act as our time machines, peering back to the cosmic dawn to see if infant galaxies were already wrapped in magnetic blankets. The answer will reveal whether magnetism is a fundamental thread in the tapestry of the cosmos, as intrinsic to the universe as gravity itself. But if the universe is fundamentally a quantum system humming with endless possibilities, why is the world we perceive so stubbornly definite? This brings us to one of the deepest and most perplexing questions in all of physics, the quantum measurement problem. It's the glaring disconnect between the bizarre, blurry rules that govern particles in isolation and the concrete, objective reality we experience every day. At its heart, this problem forces us to ask what really happens at the moment of observation, and the answer might reveal that the very act of looking is what weaves the tangled quantum potential into the single thread of our experienced reality. To appreciate this paradox, let's revisit the famous double-slit experiment, a classic demonstration of quantum weirdness. When you fire a stream of electrons or photons at a barrier with two narrow slits, they don't behave like tiny bullets, each going through one slit or the other. Instead, they act like waves, creating an interference pattern of light and dark bands on a screen behind the barrier. This pattern shows that each individual particle is somehow passing through both slits simultaneously and interfering with itself. The particle exists in a superposition of multiple states or paths. This is the core of the quantum world, a realm of potentialities and probabilities described mathematically by the wave function. Now here's where the mystery deepens. The moment you place a detector at one of the slits to see which path the particle actually takes, the interference pattern instantly vanishes. The particle suddenly behaves like a well-behaved little bullet going through one slit or the other. It's as if the particle knows it's being watched and changes its behavior accordingly. The act of measurement seems to force the particle to make a choice, collapsing its spread-out wave function into a single, definite outcome. The traditional explanation for this is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg in the early 20th century. This view draws a sharp line between the quantum microworld and the classical macroworld. It says the wave function isn't a description of a real physical state, but merely a mathematical tool that encapsulates our knowledge of the probabilities of various outcomes. In this interpretation, the collapse of the wave function isn't a physical process but a philosophical update. It happens upon measurement, but measurement is vaguely defined as an interaction with a classical apparatus. The Copenhagen interpretation essentially says, don't ask what's really happening, just use the math to predict the odds. This pragmatic approach works beautifully for making predictions, but it leaves many deeply unsatisfied, as it seems to place human consciousness or classicality at the center of reality without explaining why. Dissatisfaction with this vagueness has spawned a host of alternative interpretations, each proposing a different mechanism for how the quantum blur becomes a sharp reality. One compelling and increasingly popular view is the objective collapse theory. This idea proposes that the wave function collapse is a real physical process, not something triggered by conscious observation. It suggests there is a fundamental limit to how long a superposition can be maintained. For a single electron, a superposition could last a very long time. But for a larger, more massive object, some new physical law causes its wave function to spontaneously and rapidly collapse into a definite state. This would happen all the time, everywhere, without any need for an observer. Theories like JRW, Garadi, Rimini, Weber model this by adding a tiny, random chance per unit time for each particle to spontaneously localize. For a single particle, this chance is so small it would almost never happen. But for a macroscopic object made of trillions of particles, the probability that at least one particle will collapse becomes a near certainty, and this triggers the collapse of the entire system almost instantly. This provides a natural, objective threshold explaining why we never see cats or people in superpositions, only tiny particles. A completely different and perhaps the most astonishing solution is the many worlds interpretation we touched on earlier. It daringly eliminates the collapse altogether. In this view, the wave function never collapses. Instead, at the moment of a quantum event with multiple possible outcomes, the entire universe splits into multiple branches, each containing one of the outcomes. In the double-slit experiment, when the particle reaches the slits, the universe divides. In one branch, a version of the particle goes through the left slit and is detected. In another, equally real branch, a version goes through the right slit and is detected. There is no single outcome, there are only different versions of reality forever separated. What we perceive as the random, probabilistic nature of quantum mechanics is simply our subjective experience of being trapped in one branch of an endlessly branching multiverse. This interpretation is elegant because it removes the need for a special collapse rule, but it comes at the cost of accepting an infinite number of parallel universes. Each of these interpretations paints a radically different picture of the hidden patterns underlying reality. The Copenhagen view suggests a universe where potentiality is primary and reality is somehow created by interaction. Objective collapse theories propose a universe with a hidden threshold where quantumness gives way to classicality, perhaps pointing toward new physics that modifies quantum mechanics. The many worlds view suggests a reality of unimaginable breadth, where every possibility is realized in a vast, branching tapestry of parallel existences. The quantum measurement problem is far more than a technical puzzle for physicists. It is a profound inquiry into the nature of reality itself. forcing us to confront whether our observations create the world or simply discover a world of endless possibilities. But the delicate balance of forces and the ghostly hum of the quantum vacuum all depend on a far more fundamental condition for our existence, a single, staggering fact that allowed anything at all to form in the first place. We are here because the universe is made of something rather than nothing, and this is perhaps the most profound asymmetry of all. According to our best theories of particle physics, the Big Bang should have created equal amounts of matter and antimatter. For every proton born, an antiproton should have flashed into existence, for every electron a positron, and then, in a flash of mutual annihilation, they should have completely obliterated each other, leaving behind a universe containing nothing but a dull, uniform bath of light. No stars, no planets, no people, just photons, and yet here we are. Clearly, that is not what happened. A tiny, almost imperceptible surplus of matter over antimatter. Just 1 part in a billion somehow survived that primordial conflict. This is the Barrian asymmetry mystery, and understanding this greatest of all cosmic imbalances might reveal the hidden pattern that made our very existence possible. To grasp why this is so puzzling, we need to understand the concept of symmetry in physics. For a long time, physicists believed that the laws of nature were perfectly symmetric between matter and antimatter. This principle is known as CP symmetry, which combines charge conjugation, swapping particles for antiparticles, and parity, reversing spatial coordinates, like looking in a mirror. If CP symmetry held perfectly, the Big Bang would have been a perfectly balanced event, resulting in total annihilation. The fact that we have a universe of matter means that this symmetry must have been violated. Some process must have treated matter and antimatter slightly differently, favoring the production or survival of one over the other. The hunt for this CP violation has been one of the most intense quests in modern physics. We actually know that CP violation does occur because we've observed it in the laboratory. It was first discovered in 1964 in the decay of strange particles called kaons, a finding that earned James Cronin and Val Fitch the Nobel Prize. Later, much larger effects were found in the behavior of B mesons, but here's the crucial problem. The amount of CP violation we have measured in these experiments is far too small to account for the vast cosmic surplus of matter we see today. It's off by a factor of about 10 billion. It's like finding a single drop of water and trying to explain the existence of all the oceans on Earth. The known sources are simply insufficient. This means there must be other, much stronger sources of CP violation out there, operating under conditions we haven't been able to recreate or observe yet. The hidden pattern we're searching for is written in the fundamental laws of particle physics, but we've only read the first few words. This has led physicists to propose some of the most compelling and elegant theories in modern cosmology. One of the leading candidates is a process called leptogenesis. This theory cleverly connects the mystery of matter's dominance to another deep puzzle, the astonishingly light mass of neutrinos. Leptogenesis requires the existence of very heavy, right-handed neutrinos partners to the standard neutrinos we know, but so incredibly massive they could only have been produced in the extreme energies of the very early universe. As these heavy neutrinos decayed, the theory suggests they did so in a CP-violating way, producing slightly more matter than antimatter in the form of leptons, electrons, and neutrinos. Through a complex cascade of particle interactions known as Sphaleron processes, this lepton asymmetry could then have been converted into the Barrian asymmetry we see in protons and neutrons today. In this breathtaking narrative, the invisible, ghostly neutrino, a particle that barely interacts with anything, might be the very reason that galaxies, stars, and we ourselves exist. Its properties, and those of its hypothetical heavy sibling, could hold the key to the universe's greatest imbalance. Other theories look beyond the standard model of particle physics entirely to ideas like grand unified theories or supersymmetry. These frameworks naturally introduce new particles and forces that could have created the necessary CP violation. In these scenarios, the asymmetry could have been generated as the hot, early universe underwent dramatic phase transitions, much like water freezing into ice. Bubbles of the new phase of the cosmos would have nucleated and expanded, and on their walls, interactions could have occurred that treated matter and antimatter differently, filtering out one and allowing the other to prevail. The precise mechanics of this cosmic filtering remain hidden from us, a pattern etched into the fabric of reality at energies so high we may never directly probe them with particle colliders. The search for the answer is a dual one, fought on both cosmic and microscopic fronts. Particle physicists build immense colliders like the Large Hadron Collider, desperately searching for any new particle whose behavior might show even a hint of the required additional CP violation. Meanwhile, cosmologists use their telescopes to look back in time, measuring the properties of the primordial universe with ever greater precision, looking for any signature in the distribution of galaxies or the cosmic microwave background that might be the fossilized imprint of those first few seconds. The baryon asymmetry is not some minor curiosity. It is the fundamental question of why there is something rather than nothing. It suggests that the deepest laws of physics are not perfectly symmetrical and clean, but contain within them a tiny, built-in bias, a preference for existence over oblivion. This hidden pattern of imperfection is the reason we are here to look up at the stars and wonder about it all. Yet for all its invisible influence, dark matter is merely the sculptor of the cosmic stage, the director of the entire cosmic play. The force that sets the tempo and ultimately decides its final act is the mysterious and repulsive presence of dark energy. It is dark energy that governs the expansion rate of the universe itself, controlling how the immense canvas of space-time stretches over billions of years. In the early universe, when matter was densely packed, gravity dominated, tirelessly working to pull the cosmic web together. But as the universe expanded and thinned out, dark energy's repulsive push began to overtake gravity's attractive pull. This transition marked a fundamental shift in the evolution of the large-scale structure. Where gravity builds, dark energy inhibits. It acts as a kind of cosmic resistance, making it increasingly difficult for new filaments to form and for existing structures to pull in new material from the ever-widening voids between them. The cosmic web we see today is therefore a fossilized snapshot of a specific era, a structure that formed primarily when gravity was in charge, and whose future growth is now being steadily stifled by the accelerating expansion driven by dark energy. We are witnessing the universe at a pivotal moment, observing the grand architecture from its most active period of construction, even as the foreman has already given the order to slowly shut the job site down. This vast, interconnected celestial architecture reveals a hidden pattern far grander than any one galaxy or cluster. It shows us a universe that is not a random scattering of islands, but a single, coherent, and breathtakingly organized network. The cosmic web is the ultimate expression of gravity's patient work and dark energy's pervasive influence, a blueprint written on a scale so immense it challenges our very perception of reality. It tells us that to understand the cosmos, we cannot just study the stars, we must map the empty spaces between them, trace the invisible threads that connect them, and listen to the hidden forces that have been weaving this grand tapestry since the very beginning of time. But this profound link between observation and reality leads us to a far more controversial frontier, a place where physics meets philosophy and the very nature of mind itself. We've seen how measurement forces a quantum system to choose a state, but what if the act of observation isn't just about instruments and detectors? What if it's intrinsically tied to consciousness? This is the deeply provocative and hotly debated theory of quantum consciousness, a hypothesis that suggests our minds are not passive observers of a predetermined world, but active participants in its very creation, woven into the hidden patterns of the cosmos at the most fundamental level. The idea finds its most famous and often misunderstood roots in the early days of quantum mechanics with the Copenhagen interpretation. While Niels Bohr and Werner Heisenberg didn't explicitly put consciousness at the center, their description of the measurement problem opened the door. If a quantum system remains in a superposition until it is observed, a nagging question remains: what exactly qualifies as an observer? Is it a Geiger counter, a photographic plate, or does it require a conscious mind to finally resolve the uncertainty? Some prominent physicists like John von Neumann and Eugene Wigner argued for the latter. Wigner, in particular, proposed a famous thought experiment now known as Wigner's friend. Imagine a physicist in an isolated lab performing a quantum experiment like the Schrödinger's cat scenario. From the friend's perspective inside the lab, the wave function collapses when he looks in the box. He finds either a live or dead cat. But from Wigner's perspective outside the sealed lab, the entire system, including his friend, is still in a superposition of states until he opens the door and asks for the result. This seems to suggest that conscious awareness is the ultimate catalyst that collapses the wave function, making reality concrete. This perspective, often called the consciousness causes collapse interpretation, is both mesmerizing and deeply problematic for most scientists. It seems to place human perception on a special pedestal, resurrecting a kind of cosmic solipsism where reality doesn't truly exist until a conscious being looks at it. It also leads to an infinite regress. If a mouse looks at the experiment, does that count? What about an ant, a bacterium? The theory struggles to define what consciousness is or where the threshold for observation lies, venturing from the firm ground of physics into the murky waters of philosophy. For these reasons, it remains a fringe view in modern physics, with most researchers favoring interpretations like decoherence or the many worlds hypothesis that don't require a special role for the mind. Yet the allure of a connection persists, leading to a different, more nuanced approach: the idea that consciousness itself might be a quantum process. This is the core of renowned physicist Roger Penrose and anesthesiologist Stuart Hameroff's orchestrated objective reduction theory, or OR. They propose that the brain isn't a classical computer, as is often assumed, but a quantum computer. Their theory centers on structures inside neurons called microtubules, tiny protein cylinders that form the brain's cytoskeleton. Penrose and Hameroff suggest that these microtubules are capable of hosting quantum states, specifically superpositions of protein conformations, that are protected from their noisy, warm, wet environment long enough to perform quantum computations. According to their model, these quantum superpositions grow and then periodically collapse, a process Penrose links to a fundamental threshold in spacetime geometry. Each collapse event is a moment of objective reduction, and it is in these instantaneous moments that they propose conscious experience arises. In this view, our stream of consciousness is literally a sequence of quantum state reductions happening in the microtubules of our brain cells. The implications of this are staggering. It would mean that our thoughts, our awareness, our very sense of self are not just emergent properties of classical neural network firing, but are deeply rooted in the quantum fabric of the universe. It proposes a direct bridge between the physics of the very small and the phenomenon of subjective experience. Unsurprisingly, OR has faced fierce criticism from the scientific community. Many physicists argue that the brain is far too warm and disordered for delicate quantum states to survive for the necessary length of time without decohering instantly. Biologists point out that microtubules seem to perform more mundane structural and transport roles, with no clear evidence they can support the kind of quantum coherence the theory requires. Despite these formidable objections, the theory endures, pushing forward a research program that continues to investigate the possibility of quantum biology in the brain, a testament to the powerful intuition that the mystery of consciousness and the mystery of quantum reality might share a common solution. Whether one finds these ideas compelling or outlandish, they force a profound philosophical shift. They challenge the comforting assumption that we are separate from the universe we observe, mere spectators in a grand cosmic theater. Instead, they suggest a universe that is participatory, where the observer and the observed are inextricably linked in a dance of co-creation. The hidden pattern here is not one of cold, detached machinery, but of a reality that may be responsive in some deep and fundamental way to the act of perception itself. It paints a picture of a cosmos where mind and matter are not two separate substances, but different aspects of a single, unified whole. A pattern of existence where consciousness is not a late-arriving accident, but a fundamental feature written into the laws of physics from the very beginning. Yet for all the staggering complexity we've uncovered, from the quantum foam to the cosmic web, there remains a dream so audacious it has captivated physicists for over a century. The quest for a single, elegant framework that can explain every force, every particle, and every interaction in the cosmos under one mathematical roof. This is the search for a theory of everything, a final theory that would reveal the most fundamental hidden pattern of all, the underlying principle from which all of reality unfolds. It's a pursuit that seeks to heal the deepest fracture in modern physics, the glaring incompatibility between the two monumental pillars of our understanding, the quantum world, which governs the very small with its probabilities and particles, and the relativistic world, which describes the force of gravity and the large-scale structure of spacetime. Unifying these seemingly opposed descriptions of reality is the greatest challenge in all of science, and the potential paths toward it are as breathtaking as they are bizarre. One of the most prominent and mathematically sophisticated paths is string theory, and its most ambitious extension, M-theory. We've touched on how string theory replaces point-like particles with tiny, vibrating loops, but its true goal is far grander. The theory naturally describes not just matter, but the forces acting upon it, including gravity. Different vibration patterns of the strings correspond to different particles. One note might be an electron, another a photon, and another the graviton, the hypothetical quantum particle of gravity. This is its stunning promise, a single type of fundamental object, the string, giving rise to the dizzying diversity of the universe. Yet as physicists delved deeper, they found not one but 5 distinct, self-consistent versions of string theory. This was deeply troubling for a theory claiming to be unique and fundamental. The resolution came with a revolutionary leap in the 1990s when physicist Edward Witten proposed that these 5 theories were not competitors, but merely different facets of a single, deeper, 11-dimensional framework he called M-theory. In this conception, the 5 string theories are like different shadows cast by a single, higher-dimensional object. Much like a 3-dimensional cylinder can cast either a rectangular or circular shadow depending on the angle of light. M-theory remains largely mysterious. The M can stand for membrane, magic, or mystery, but it suggests our universe may be a 4-dimensional membrane floating within an 11-dimensional reality, with strings being merely 1-dimensional slices of higher-dimensional membrane. The hidden pattern it seeks to reveal is one of ultimate unity, where all forces and particles emerge from the vibrational modes of these multidimensional objects. But not all physicists are convinced that adding more dimensions is the right approach. A powerful and compelling alternative insists that we must quantize space and time themselves, not just the objects within them. This is the goal of loop quantum gravity. Unlike string theory, LQG makes no attempt to describe all the forces at once. Instead, it focuses squarely on gravity, aiming to rewrite Einstein's general relativity in the language of quantum mechanics. Its core, radical idea is that space is not a smooth, continuous background as Einstein described, but is instead composed of tiny, discrete, indivisible grains. Think of the fabric of spacetime not as a perfectly smooth sheet, but as an incredibly fine mesh or a network of a billion tiny loops. These loops or threads of spacetime are woven together into a dynamic, evolving structure called a spin network. The theory provides a natural minimal unit, the Planck area and the Planck volume. You cannot have half a unit of space. It is pixelated, much like a digital image appears smooth from a distance but reveals its discrete pixels when you zoom in. This elegantly avoids the infinities that plague other quantum gravity approaches and offers a breathtaking vision of the Big Bang. In LQG, there is no singularity, no point of infinite density. Instead, the collapsing universe of a previous cycle would reach a point of maximum density and then bounce back out, giving rise to our expanding universe. The hidden pattern here is not one of vibrating strings, but of a woven, combinatorial geometry of space itself, a cosmic tapestry where every knot and loop defines a quantum of reality. Beyond these two giants, other fascinating paths are being explored. Causal dynamical triangulations uses powerful computer simulations to treat spacetime as being made of tiny, simple geometric building blocks, then lets the rules of quantum mechanics determine how they assemble. Remarkably, this approach shows that a smooth, four-dimensional universe can spontaneously emerge from this chaotic quantum soup, much like the ordered structure of a crystal emerging from the random motion of molecules. Another approach, called the amplituhedron, suggests that the seemingly complex probabilities of particle collisions might be calculated from the volume of a beautiful, multi-dimensional geometric object, potentially rendering the concepts of space and time as derived, emergent properties rather than fundamental stages. Each of these frameworks, from the extra dimensions of M-theory to the quantum loops of LQG, represents a different bet on what the ultimate hidden pattern of the universe might be. They are all attempts to read the cosmic code, the fundamental software that the universe is running. The implications of discovering such a theory are almost beyond comprehension. It would represent the end of a millennia-long journey to understand the fundamental nature of reality, a culmination of human curiosity. It could allow us to peer beyond the Big Bang, to understand the true origin of the cosmos and its possible fate. It might reveal whether other universes are inevitable or impossible, and finally provide a true mechanical understanding of why our universe has the particular set of laws and constants that it does. It could answer the question of whether mathematics is invented or discovered, and show us if the breathtaking beauty and elegance we find in physical law is a necessary feature of any consistent reality. The search for a theory of everything is more than a technical pursuit. It is a fundamental human endeavor to find our place in the cosmos by understanding the deepest, most hidden pattern of all, the single, simple, and profound rule from which everything, including us, must flow. From the holographic projection of our reality to the eternal cycles of conformal cosmology, and from the cosmic web shaped by dark matter to the quantum foam churning beneath our feet, we have journeyed through a breathtaking landscape of ideas. Each theory, in its own unique way, proposes a fundamental architecture for existence, a hidden pattern waiting to be decoded. Some suggest the universe is a cosmic computer, a magnificent simulation running on incomprehensible hardware. Others argue it is a mathematical structure, its laws the inevitable outcome of abstract logic. There are theories that place consciousness itself at the center of reality, while others see our awareness as a beautiful but accidental byproduct of complex computation. What is so incredible is that these aren't just wild speculations. They are serious, compelling attempts to answer the most profound questions we can ask, using the best tools of mathematics, physics, and philosophy. They represent the absolute frontier of human curiosity, a testament to our relentless drive to understand our place in the grand scheme of things. What this incredible diversity really shows us is that reality is far stranger, more complex, and more wonderful than our everyday experience suggests. The solid ground beneath your feet, the steady flow of time, the very stars in the sky, they might all be surface-level illusions, emergent properties of a far deeper and more mysterious underlying order. Whether it's the fine-tuned constants that allow for our existence, the ghostly connections of quantum entanglement, or the invisible scaffolding of dark matter, these hidden patterns are the universe's way of whispering its deepest secrets to those who are willing to listen. They challenge us to think bigger, to question our assumptions, and to marvel at the fact that we are even capable of contemplating such grand and beautiful ideas. This isn't about finding one single answer. It's about expanding the conversation, about appreciating the multitude of ways we can interpret the cosmic data we have. As we reach the end of this exploration, I want to turn the question over to you. Which of these hidden patterns resonates most deeply with your own intuition about reality? Does the elegant simplicity of the universe as a mathematical structure feel right to you? Or does the participatory nature of a conscious cosmos, one that comes into being through observation, seem more compelling? Perhaps you're drawn to the cosmic democracy of the multiverse, where every possible reality exists somewhere, or maybe you find the intricate, fractal self-similarity of the cosmic web to be the most beautiful pattern of all. There are no wrong answers here, only different ways of connecting with the profound mystery of it all. This is a conversation that belongs to all of us, so I'd love to continue it together. Let me know in the comments which theory you find most fascinating and why. What hidden pattern do you think holds the key to understanding our universe? Your perspective is a valuable part of this ongoing, incredible human quest for understanding.